Welcome to the Sleepy Scientist. This is your quiet corner of the evening, where the noise of the day fades and the universe takes a slower breath. Wherever you are, lying beneath soft lamplight, tucked into bed, or just letting the mind drift, I'm glad you found your way here. Tonight's calm journey explores one of the most beautiful puzzles in all of physics. Why does space bend? Before we begin, I'd love to know, where in the world are you listening from? It's always fascinating to imagine this same stillness stretching across oceans and continents, connecting night skies everywhere. And if you're new here, a gentle reminder. A like and a subscribe really help this channel grow and reach more sleepy minds who enjoy drifting off to science. If you're already part of this little community, thank you. It means more than you might think. Don't forget to tap the notification bell so you won't miss the next quiet journey through the cosmos. I do hope this video isn't too interesting that it keeps you awake, but if it does, at least you'll fall asleep a little wiser than before. So let's begin, softly, with a question that has puzzled scientists for over 100 years. What if gravity isn't a force at all, but the shape of space itself? For as long as humans have watched the night sky, they've seen motion everywhere. The moon slides across its dark sea, the planets trace silent patterns, and the stars seem fixed yet eternal. For most of history, this dance was explained by invisible pulls, gravity as a mysterious hand reaching across emptiness. It worked beautifully. But as we learned to measure time and motion more precisely, something strange began to show through the cracks. Every object, from a falling apple to a speeding planet, seemed to obey the same rule. They all fell alike, heavy or light, large or small. Each moved as if the universe itself were choreographing their steps. The question was, why? Why would gravity treat everything equally? Why would light, which weighs nothing at all, bend around a star as if it too were following a path set out for it? In the early 1900s, a quiet revolution began. A young patent clerk named Albert Einstein suggested that gravity might not be a force pulling downward, but rather a change in the shape of space and time themselves. Matter, he said, tells space how to curve, and space tells matter how to move. It was a sentence so simple that it hid an entirely new vision of reality. This idea would transform how we understand orbit, starlight, and even time itself. It showed that the universe isn't a stage where things move. It's a living fabric that bends, stretches, and ripples. Tonight we'll drift gently through that fabric, seeing how curvature creates everything we experience as gravity. We'll explore how falling can be a form of freedom, how clocks run at different rhythms, how light itself bends around stars, and how space can even ring like a bell when great masses collide. There's no rush, no math, and no pressure to remember anything. Just let the ideas unfold slowly, like constellations forming in the dark. By the end, the cosmos may feel a little less like a place of forces, and more like a poem written in geometry. So settle in. The night is quiet, the universe patient, and somewhere beneath the curves of space, every star is part of the same graceful design. For centuries, gravity was understood as a kind of invisible handshake between objects, a steady, dependable pull that reached through the void. Sir Isaac Newton gave it a language that worked astonishingly well. With his laws, you could predict the path of an apple falling from a branch or the arc of the moon around the Earth. The same equation that described a pebble's fall could chart the orbit of Jupiter. The universe, it seemed, had been tamed by mathematics and reason. In Newton's world, every object with mass tugged on every other object no matter how far apart. The pull weakened with distance but never vanished completely. It was a vision of harmony and universality, every atom whispering to every other atom across infinite space. For over 200 years, that idea reigned supreme. Engineers, sailors, and astronomers all built their confidence on it. If you knew the masses and distances, you could predict the future of planets themselves. But even in Newton's time, there was a small question lurking in the background. How exactly did this pulling happen? Newton himself admitted he didn't know. He called it action at a distance, a force that leapt invisibly across emptiness. It worked perfectly in the equations, but not in the imagination. Nothing seemed to travel between the Earth and the Moon. No rope, no wind, no particle carrying the message. Gravity, it seemed, acted faster than thought itself. Still, no one argued with success. The predictions fit reality so beautifully that most people simply accepted the mystery as part of nature's design. Then, as centuries passed and instruments improved, scientists began to notice something deeply curious. Every object, regardless of its weight or shape, fell in exactly the same way. A hammer and a feather would land together if the air were gone. A cannonball and a coin follow the same path. This was more than coincidence, it was a clue. Why would heavy and light things move identically if gravity were a pull proportional to mass? Shouldn't the larger object with more gravitational charge behave differently? The answer lay not in forces, but in geometry. The equality of free fall hinted that everything, no matter its mass, was following the same kind of path through space and time. It wasn't being yanked downward, it was simply moving naturally along the shape of reality itself. By the late 1800s, cracks were appearing in Newton's grand clockwork. Precise measurements of Mercury's orbit showed a tiny, persistent drift that Newton's equations couldn't quite explain. The difference was minute, just a few dozen arc-seconds per century, but unmistakable. Something in the way gravity worked wasn't fully captured by the old rules. Meanwhile, new ideas about light and energy were reshaping physics. The stage was set for a revolution, and it would arrive not through a laboratory but through thought. In the year 1905, a young patent clerk named Albert Einstein published a series of papers that would change the world. In one of them, he proposed that the laws of physics are the same for everyone, no matter how fast they're moving, and that the speed of light never changes. That simple statement led to special relativity, the first step in understanding time and space as part of the same fabric. Then, just a few years later, Einstein took a deeper look at gravity itself. He asked a question that no one else had dared to take seriously. What if gravity isn't a force at all? What if it's the shape of space and time bending around matter? Imagine a heavy object resting on a stretched rubber sheet. The sheet curves, and smaller objects rolling nearby naturally follow the curves, not because they're pulled by a string, but because that's simply the easiest path available. Replace the sheet with space-time itself, and you have Einstein's insight in miniature. Matter tells space how to bend. Space tells matter how to move. This was more than a mathematical trick. It solved the problems Newton had left behind. Gravity no longer needed to act instantly across distance. Its influence moved through space-time as ripples, limited by the speed of light. Every planet, star, and grain of dust followed the same graceful path, because all were tracing the same geometric rule written into the universe. Free fall was no longer being pulled, it was motion along the natural lines of curved space-time. Einstein's vision was tested and tested again. It explained Mercury's wandering orbit perfectly. It predicted that light would bend when passing near the Sun, a forecast proven right during a solar eclipse in 1919. It predicted that time itself would slow near massive objects, a fact confirmed decades later with atomic clocks and satellites. Each success deepened the realization that gravity was not a mysterious force whispering across space. It was the quiet curvature of reality itself, and that curvature is subtle. The Earth bends space and time only slightly. You'd need a black hole to twist it enough to notice without instruments. But even here, every step, every falling leaf, every orbit of the moon follows the same law. Not because Earth pulls with invisible hands, but because space and time together form a landscape with valleys and hills, and everything moves according to that terrain. Einstein's equations, written in 1915, are famously dense, but their meaning is poetic. They say that the distribution of matter and energy determines the geometry of the universe. Where there's mass, space curves. Where there's energy, time stretches. A simple idea, wrapped in deep mathematics. Gravity is not an external command. It's the universe responding to itself. The beauty of this picture lies in its gentleness. It doesn't replace Newton's gravity so much as complete it. Newton's theory still works beautifully for bridges, baseballs and planets. Einstein's is simply more precise, stretching seamlessly from the smallest orbit to the curve of the cosmos itself. And all of it rests on a change in perspective, a decision to stop thinking of gravity as a tug and start seeing it as a pattern. You could say that gravity isn't magic, it's just very polite geometry. Matter quietly asks space-time to make room, and space-time obliges by bending ever so slightly. The result is the graceful motion of planets, the soft fall of an apple, and the subtle slowing of time. It's a universe that doesn't shout, but whispers in curves. Imagine standing in a small elevator somewhere in deep space, far from any stars, planets, or even the faint pull of a comet. You're floating, suspended in perfect stillness. If you let go of a key, it drifts beside you. There's no up, no down, no sense of weight, only the quiet hum of nothingness. This, Einstein realized, is what the true absence of gravity feels like. Not falling, not being pushed, simply existing in motionless freedom. Now imagine the same elevator, but this time it isn't floating in space. It's been cut loose, falling freely toward the surface of the Earth. The cables have snapped, but inside something curious happens. You let go of your key again, and once more it floats beside you. The floor doesn't press up on your feet, your arms feel light, and the sensation of weight disappears. The falling elevator and everything in it are all accelerating together at the same rate. So inside, it's as though gravity has been switched off. This is the heart of Einstein's great insight. Locally, falling freely in a gravitational field feels the same as drifting weightless through empty space. It's called the equivalence principle, and it sounds simple enough to write on a coffee mug, but it contains the seed of the entire theory of general relativity. To Einstein, this was not a mathematical curiosity. It was a clue to how the universe really works. Inside that falling elevator, the person, the key, and the feather are all moving together along the same curved paths that space and time dictate. None of them feel a force because, in a sense, there isn't one. Gravity, in this picture, isn't pushing or pulling. It's simply guiding motion along the natural geometry of space-time. What you feel as weight when you stand on solid ground isn't gravity itself, but resistance. The floor stops your body from following its natural free-falling path. Einstein's imagination lingered in that elevator for years. He pictured what would happen if it were sealed, with no windows or instruments giving away its location. Could you tell whether you were drifting in the still emptiness of space or falling freely toward a planet? You couldn't. Every experiment inside, tossing a ball, floating a feather, or even shining a beam of light, would behave identically. The laws of physics inside a freely falling frame were indistinguishable from those in the weightless void. That, to Einstein, was not coincidence. It was revelation. He called it the happiest thought of my life, because if gravity could vanish inside a falling room, then gravity must not be a true force at all, but a kind of illusion that arises when motion is prevented. When you fall freely, you're following the natural flow of space-time. When you stand still, it's the ground beneath you that exerts a force, not the Earth pulling on you. Think of an astronaut orbiting the Earth. From the ground, it looks like they're constantly falling. From their perspective, they're in endless free fall around the planet, never hitting the surface because the ground keeps curving away beneath them. Inside their capsule, they float, not because gravity is gone, but because everything inside is falling together at the same speed. Gravity hasn't vanished, it's simply stopped opposing them. This idea also explains why being pressed into your seat during takeoff feels the opposite of floating. In that moment, you're being pushed upward by the rocket's thrust, while gravity is trying to let you fall. The push is what you feel as weight. It's resistance again, the denial of free fall. Once the engine's cut and the spacecraft coasts freely, that resistance vanishes, and so does your weight. Einstein realized that this equality between acceleration and gravity, between falling and drifting, couldn't be a coincidence. It meant that gravity and acceleration were deeply connected. In a small enough region of space and time, you could always find a point of view where the laws of physics look the same as they did in empty space. That's what locally flat means. The world might be curved overall, but in small neighborhoods, it's flat enough that you can pretend gravity doesn't exist. The difference appears only when you zoom out, step back far enough, and the illusion of flatness fades. Over large distances, free-falling paths that start parallel begin to converge or diverge. That's curvature. Space-time bending under the influence of mass and energy. The beauty of Einstein's elevator is that it works as a bridge between the local and the global. Inside, you feel no gravity. Outside, the curvature of space-time shapes your motion. It's easy to mistake this as an abstract thought experiment, but it's something we experience constantly. Every time a skydiver leaps from a plane, their stomach's brief flutter isn't fear. It's geometry. They're in a small, temporary bubble of freedom, moving along the path Earth's curvature dictates. They feel weightless because for those few seconds they are. When the parachute opens and the straps tighten, the sensation of gravity returns. But what's really returned is the resistance of the air and the harness against their natural motion. The same principle explains why astronauts orbiting hundreds of kilometers above Earth are not outside gravity's reach. They're deep within it. Their continuous fall just never ends. The floor of their spacecraft no longer pushes up on them, so their bodies move freely along the paths that space-time prescribes. The result feels like floating, but it's really falling perfectly, endlessly, and peacefully. Einstein's elevator gave physics a new way to think about motion. Instead of seeing gravity as an invisible pull, he redefined it as the natural result of living in a curved universe. If you remove all resistance, floors, cables, and rockets, you discover that everything moves freely and gracefully, following the geometry written by matter and energy. That's what free fall really means. Motion with nothing in the way. The quiet inside the falling cabin isn't just a metaphor for physics, it's a window into how the universe behaves when left alone. Every galaxy, star, and planet follows its own free-falling path through the fabric of space-time. What we call gravity is simply the shape of those paths written large across the cosmos. And somewhere in that silence, in that drifting elevator or the orbiting capsule, lies one of the most profound truths ever uncovered. The feeling of weight is not the presence of gravity, but the absence of freedom. If space were just a three-dimensional stage where things move and time was simply a ticking clock keeping score, the universe would be easy to picture. But the truth is far stranger and far more elegant. Space and time are not separate ingredients. They are threads of the same cloth. Pull on one and the other moves. compress time and space stretches, twist space and time bends with it. This woven entity is called space-time, and it's the stage, script and motion all in one. To understand why, it helps to think about how we describe anything that happens. Every event, whether it's a supernova exploding, a raindrop falling, or you blinking your eyes, can be pinpointed only when we know both where and when it occurred. A location alone isn't enough. If you say the moon, that doesn't mean much unless you say when the moon was there, because it's constantly moving. Time is the fourth coordinate that makes every moment unique. Together, the trio of spatial dimensions and the single dimension of time give every event its complete address in the universe. This simple idea that where and when are inseparable was what led Einstein to unite space and time into a single structure. The concept sounds abstract, but you live it every day. When you move through space, you also move through time. If you stand perfectly still, you're travelling only through time, 1 second per second, steadily forward. When you start walking, a small part of that forward motion through time gets traded for motion through space. You don't notice the exchange because the speed of light is so vast that your share of it is minuscule. But the trade is there, quietly balancing every journey you take. Space-time has its own geometry, and it's different from the geometry you learnt in school. In everyday geometry, the shortest path between 2 points is a straight line. In space-time, the shortest path between 2 events is the one that takes the least effort, considering both distance and duration. That path is called a world line, a continuous thread showing where and when something exists. A resting object's world line points straight up through time. A moving object's world line tilts slightly, blending space and time together. The faster something moves, the steeper the tilt, until, for light itself, the line lies perfectly diagonal, the ultimate speed, the limit that no one can surpass. This is where the idea of intervals comes in. In ordinary life, distance and time are measured separately. You might say 2 towns are 30 kilometers apart, or that a trip takes half an hour. But in space-time, those numbers merge into one single quantity. The space-time interval. It's like combining space and time into a single distance that everyone agrees on, even if they disagree about the separate pieces. 2 observers moving at different speeds might not agree on how long something took or how far it was, but they'll always agree on the interval between events. That's the cosmic compromise. Reality reshuffles space and time depending on motion, but it keeps the combined truth the same. If this feels mind-bending, you're in good company. Early physicists wrestled with it too. They found comfort in something called the light cone, a way of visualizing what events can and cannot influence each other. Imagine a bright flash in space, a single spark like a camera bulb in the dark. Light spreads outward in every direction at the same speed, forming an ever-expanding sphere. Draw that expansion through time, and it looks like a cone rising upward. Everything inside that cone can, in principle, be reached by the light from the spark. Everything outside it is forever out of reach. That's nature's way of enforcing order. Causality. Nothing can travel faster than light because nothing can move outside its cone. It's the universe's gentle rule for keeping time from contradicting itself. The light cone also shows why the past, present and future are more than just words. Events inside the cone behind you are your past. They could have affected you. Events inside the cone ahead of you are your future. You could still affect them, but anything outside both cones is simply elsewhere, beyond influence. A galaxy 1 billion light-years away could be shining right now, but its present light won't reach Earth for another 1 billion years. In a sense, it's now, and your now are disconnected. The universe keeps each patch of space-time honest to its own timeline. All of this might sound like abstract geometry, yet it describes something profoundly physical. Clocks, for example, don't all tick the same way. A clock on a fast-moving satellite runs slightly slower than one on Earth, not because it's broken, but because its path through space-time is different. Similarly, a clock near a massive planet ticks more slowly than one farther away, because mass curves space-time, changing how time itself flows. It's as though each object is walking on a flexible surface that bends and stretches depending on energy and mass. You can picture space-time as a vast fabric with time running vertically and space stretching horizontally. Every object, planets, people, light beams, is a thread weaving through it. Massive objects press down on the fabric, bending nearby threads toward them. Those bends are what we call gravity. If you could look at Earth's contribution to this tapestry, you'd see time flowing slightly slower near the surface than high above, and space ever so gently curved. This visualization isn't perfect. Space doesn't literally sag like a trampoline, but it captures the idea that geometry replaces force. Where Newton imagined invisible strings pulling on distant objects, Einstein replaced those strings with curves and slopes in the fabric of space-time. The Earth moves around the Sun not because it's pulled, but because it's following the straightest possible path through a curved geometry. The Sun's mass tells space-time how to bend, and space-time tells Earth how to move. The beauty of this unification is that it removes the need for mysterious connections across emptiness. Nothing reaches out instantly. Everything communicates through the structure of space-time itself. Light acts as the ultimate referee, setting the fastest possible pace for cause and effect. No matter who you are or how you move, the speed of light stays the same, and the shape of your personal light cone tells you what's possible. Space-time isn't an invisible background, it's an active participant. When massive stars collapse or galaxies collide, the fabric doesn't just sit there, it ripples. When black holes twist, space-time swirls. When light travels, it rides the fabric itself. Every second of every life unfolds along a tiny piece of this cosmic weave. Einstein's merging of space and time gave the universe continuity. It's no longer a stage where events happen. It's the script and the stage combined. A dynamic fabric in which matter and motion are inseparable. Time doesn't flow separately from space. It flows through it, shaped by gravity and motion. That's why we can't fully speak of space, or time alone. They're threads of one vast tapestry. So the next time you look up at the stars, imagine them not scattered across emptiness, but stitched into an enormous fabric, every thread vibrating gently, every moment connected by geometry. Space and time are partners in the same cosmic dance, turning every falling apple and every drifting galaxy into part of one continuous story. A story written, quite literally, in curves. When we think of a straight line, we usually imagine something simple, a ruler's edge, a laser beam, the shortest path from one point to another. But in a curved universe, straight becomes a matter of perspective. On a sphere, for instance, the shortest path between two cities isn't a flat line on a map, but a curve known as a great circle. Airplanes follow these routes every day, arcing gently over the poles because that's the most efficient path, even though it looks curved on a flat chart. This idea, what it means to be straight when the surface itself is curved, is at the heart of understanding gravity and motion in Einstein's universe. In space-time, the equivalent of a straight line is called a geodesic. It's the path that takes the least effort, the most natural route an object can follow through the four-dimensional fabric of space and time. A planet orbiting a star, a satellite circling the Earth, even a beam of light passing near a massive object. All of them follow geodesics. There's no pushing, no pulling, no mysterious force tugging them off course. They simply glide along the curved geometry that matter and energy create. You can think of a geodesic as nature's path of least resistance. A marble rolling freely across a smooth surface doesn't choose where to go. It follows whatever contour the surface gives it. The same happens in space-time. When you're falling freely, with no engine or rocket or floor pushing against you, you're following a geodesic. That's why astronauts floating inside the International Space Station feel weightless. They haven't escaped Earth's gravity. They're simply moving along the natural curve of space-time around Earth, falling perfectly and perpetually. If the Earth weren't there, that path would be a simple straight line through space. But Earth's mass gently bends space-time, turning that straight line into a graceful arc. To the astronauts, the world feels still and serene. To an observer on the ground, they're in constant motion, looping endlessly around the planet. Two perspectives, one reality, a straight line in curved space-time. This concept may sound abstract, but it's deeply intuitive once you let go of the idea that space must be flat. Picture yourself walking across the surface of a globe. You start at the equator and head north along a line of longitude, trying your best to walk straight. To you, your direction never changes, yet from above your path curves toward the pole. If two people start at the equator side by side, walking north along neighbouring longitudes, they begin close together but eventually meet at the pole. Neither of them ever turned, but their paths converged. That subtle drift between nearby straight paths is the essence of curvature. In Einstein's language, this is called geodesic deviation. It's how we detect the presence of curvature, by watching how two free-falling objects that start parallel begin to move together or apart over time. In a flat world, they'd stay perfectly aligned forever. In a curved one, their separation tells us how space-time bends. You don't need fancy equations to imagine it. Just think of two boats drifting on an ocean. At first, the water seems flat and calm, but as they travel, currents pull one slightly faster, the other slower. Their paths, which began parallel, now diverge. Neither boat did anything special. The shape of the ocean did. The same idea plays out across the universe. Two asteroids passing near Jupiter will have their trajectories ever so slightly altered, curving differently depending on their starting positions. Their motion reveals the planet's mass not because it pulls on them directly, but because it shapes the geometry of the space they move through. The geodesics they follow gently twist, like threads in a woven cloth bending around a knot. Even light obeys this rule. When a beam of starlight passes close to the sun, it bends, not because the sun reaches out to grab it, but because the geometry of space-time near the sun is curved. Light always follows the straightest possible route, but in a curved universe, even the straightest path can look like a curve from afar. The stars that astronomers see near the sun's edge during an eclipse are slightly displaced, their light bent along those geodesics. It's nature's own lensing, written into the structure of reality. One of the most elegant aspects of geodesics is how democratic they are. Massive or massless, large or small, everything follows them. A planet, a photon, a grain of dust, all move along paths determined solely by the geometry of space-time, not by their size or composition. That's why, on the moon, a hammer and a feather fall side by side. They're not obeying a command from gravity. They're following the same natural route through the same curved geometry. Understanding geodesics also helps explain why astronauts and satellites appear to float even while surrounded by gravity. The International Space Station, for example, orbits about 400 kilometers above the Earth, moving at over 27,000 kilometers per hour. It's constantly falling toward the planet, but the ground beneath keeps curving away at just the right rate. Inside, everything falls together. The crew, the air, the equipment. So no one feels a thing. They're travelling along a shared geodesic, guided by Earth's curvature, free from any sensation of weight. You can imagine the same principle on a smaller scale. toss a set of keys upward and watch them arc back down. To you, it looks like a neat parabola, a temporary flight and a fall. To space-time, it's a continuous curve along a geodesic, straight when seen in the right four-dimensional light. The keys don't switch direction halfway through, they simply trace the path the geometry dictates. What makes geodesics so powerful is that they describe motion without invoking forces. The word gravity becomes shorthand for the shape of space-time. When we say an apple falls to the ground, we're really saying it's following a geodesic that leads to the centre of the Earth's curved geometry. When we say the moon orbits the Earth, we're describing another geodesic, one that happens to close back on itself, forming a stable loop. Gravity in this view is geometry experienced in motion. It's humbling to realise that every movement we make, every step, every leap, every orbit, is a thread in this vast geometric web. The shape of the cosmos determines the story of motion, and we, without even trying, follow its lines. The next time you see a leaf drifting on a stream, notice how it glides effortlessly along the current, adjusting to every bend in the river without thought or struggle. That leaf is following a geodesic, tracing the natural flow of the water beneath it. In the same way, planets and light and even you are all drifting along the currents of space-time. So when someone says that objects move in straight lines, they're not wrong, just incomplete. Straightness depends on the surface beneath. In a flat universe, lines stay apart forever. In a curved one, they meet, cross, and diverge, shaping the patterns of orbits, tides, and galaxies. The Earth, the stars, and the light between them all trace these quiet, graceful lines. The universe may look chaotic, but at its core it's guided by the simplest rule imaginable. Everything moves straight ahead, and it's the shape of space itself that decides what straight really means. Time has a rhythm, but it isn't universal. It doesn't march forward at the same steady pace everywhere in the cosmos. It bends, stretches, and slows depending on where you are and how much gravity you're surrounded by. This isn't just poetic exaggeration, it's measurable, precise, and deeply woven into the nature of space-time. The stronger gravity is, the slower time flows. Mass bends not only space, but the flow of moments themselves. It begins with energy. According to Einstein, energy and mass are two sides of the same coin. Anything that carries energy, be it a planet, a beam of light, or a handful of starlight dust, contributes to gravity. Where energy pools, space-time curves, and where space-time curves, time itself ticks more slowly. This means that near any massive object, from a planet to a black hole, clocks run ever so slightly behind those farther away. The effect is tiny on Earth, but across the universe, it becomes one of the grand rhythms that shape reality. You can test this without ever leaving home. Imagine two identical clocks, one resting at sea level, the other on a mountaintop. Both tick in perfect unison when synchronized. But as the days pass, the mountain clock pulls ahead, gaining a few nanoseconds every 24 hours. The difference is absurdly small, yet undeniably real. Time runs a little faster up there because gravity is weaker. The higher clock feels less of Earth's curvature tugging at it. Down by the sea, where Earth's gravity is slightly stronger, time slows by the tiniest fraction. The difference would never matter to a wristwatch, but to a satellite, it's everything. Your smartwatch, if it could talk, might be quietly proud of this fact. If you climbed a tall hill, it could brag that it's running ahead of every clock in the valley by a few trillionths of a second. The higher you go, the less gravity holds you, and the faster your seconds stretch out. At the summit, you're aging fractionally faster than the people standing at the beach. Not enough to earn any wisdom points, but measurable all the same. The idea that gravity can slow time isn't just theory, it's been confirmed over and over again. In the late 1950s, physicists Robert Pound and Glenn Rebka ran a beautifully simple experiment in a Harvard University tower. They placed a source of gamma rays at the top and a detector at the bottom. Because the rays had to fall through Earth's gravitational field, their light was slightly blue-shifted. Its frequency increased, meaning time at the bottom ticked just a hair slower. The difference was minute, but the instruments caught it perfectly. Einstein's prediction was right again. Decades later, atomic clocks made these tests even sharper. In one experiment, 2 of the world's most precise clocks were synchronized. One was left on the ground, the other was flown in a jet for a few hours and then brought back. When compared, the airborne clock had ticked slightly faster, just as relativity predicted. Similar results were found using rockets and satellites. No matter how many times the tests were run, the message was the same. Time is elastic and gravity gently stretches it. It's easy to take time for granted because our senses can't detect its shifts. You don't feel the seconds slowing when you step into a valley, and your heart doesn't beat faster on a mountain. The effect only shows up when we measure with extraordinary precision atomic clocks counting vibrations of cesium atoms so steadily that they could keep perfect time for millions of years without losing a second. Yet, even with that stability, gravity wins. A height difference of just a few tens of centimeters can now be detected in time dilation. That's how sensitive our instruments have become. Modern clocks can literally feel the curvature of the Earth. But what happens when you push this idea to extremes? Near massive stars or dense objects like neutron stars, the slowdown of time becomes staggering. A neutron star packs more mass than our Sun into a sphere barely 20 kilometers wide. Its gravity is so intense that time near its surface slows to a crawl compared with time farther away. If you could hover safely above it, which you can't, but imagine, seconds for you would pass while minutes or even hours might pass for someone watching from afar. The star doesn't just warp space, it kneads time itself into new shapes. And then, of course, there are black holes, the champions of gravitational time distortion. Near a black hole's event horizon, time slows so dramatically that, from the viewpoint of a distant observer, it appears to stop altogether. Light climbing out of that region stretches endlessly, losing energy until it fades to invisibility. To an outside observer, nothing ever truly falls in. It just slows, redder and redder, forever on the brink. From the perspective of the falling object, however, everything feels perfectly normal. It crosses the horizon in finite time, unaware that, from the outside universe's point of view, it is practically frozen in place. 2 perspectives, both correct depending on which part of space-time you call home. This isn't science fiction. It's the architecture of reality. Even our technology depends on it. The global positioning system, those small satellites orbiting high above, must constantly account for both their speed and their height. Moving quickly slows their clocks slightly. Being farther from Earth's gravity speeds them up. The 2 effects nearly cancel, but not quite. Engineers must correct for a difference of about 38 microseconds each day. That may not sound like much, but without the correction, GPS positions would drift by several kilometers in less than 24 hours. Your phone's map would show you walking through walls or driving across rivers. These same principles ripple through the universe. In the cores of galaxies, where supermassive black holes sit like heavy anchors, time moves at a different tempo than it does between the stars. Even on Earth, time isn't uniform. It runs faster in skyscrapers than in subways. Every clock from your wrist to the heart of the Milky Way ticks according to the gravity it feels. We live in a universe where every place has its own tempo, its own local rhythm. Einstein's equations didn't just redefine gravity, they redefined time itself. Before him, time was the great constant, the same for everyone, everywhere. After him, it became dynamic, personal, and curved. The deeper you are in a gravitational field, the more space-time is stretched, and the slower your seconds unfold. The stronger the curvature, the heavier the hand that holds the clock. There's something oddly comforting about that. Time isn't an unyielding metronome. It's supple, responsive, and alive to its surroundings. It listens to mass, to energy, to motion, and quietly adjusts. The universe doesn't keep a single time. It lets every corner breathe at its own pace. So yes, your smartwatch really would get a little smug at altitude. It's not just higher, it's ahead, ever so slightly. Somewhere, deep in that tiny circuit, it's ticking in proud defiance of gravity's gentle hold. And while you won't feel the difference, those nanoseconds matter to the satellites above, to the signals that guide your path, and to the scientists measuring the pulse of the cosmos. Time stretches softly around you every second of every day. A quiet reminder that even the most constant thing in the universe still knows how to bend. Light is tireless, but not invincible. When it climbs away from a massive object, it pays a price for its escape. It loses a little energy, stretches its wavelength, and its colour drifts ever so slightly toward the red end of the spectrum. This gentle stretching of light is called gravitational redshift, and it's one of the quiet signatures of curved space-time. To the universe, it's a simple rule. Where gravity is strong, light must work harder to leave, and even light can grow weary. Imagine a photon born near the surface of a star. It begins its journey upward, carrying energy in the form of a short, tight wavelength, perhaps blue or violet. As it rises, the star's gravity tugs on it, not in the way it would tug on a falling apple, but through the geometry of space-time itself. Climbing away from the curve, the photon must spend part of its energy just escaping. But light can't slow down. It always travels at the same cosmic speed limit. The only way to spend energy without changing speed is to change colour. Its wavelength stretches, its frequency lowers, and its hue slides toward red. By the time it reaches the empty void beyond the star, it's the same light, just slightly older, slightly longer, slightly tired. This is different from the redshift caused by motion or expansion. In a Doppler redshift, light stretches because the source is moving away, much like the drop in pitch when a train whistle passes by. The waves are literally stretched out in transit because the emitter is retreating. A cosmological redshift, on the other hand, happens because the universe itself is expanding. Space grows between galaxies, carrying the light with it, like paint stretching across a balloon. Gravitational redshift is subtler. The source may stand perfectly still, but space-time itself is curved in such a way that climbing away from mass is like hiking uphill, through molasses. It's not about movement through space, but movement through gravity's gradient. This effect is everywhere, even if we rarely notice it. Light leaving the surface of Earth, for instance, is redshifted by an almost imperceptible amount, just a few parts in a billion. But in the intense gravity of a white dwarf or a neutron star, the difference becomes enormous. The dense mass bends space-time so sharply that light leaving its surface can lose a noticeable chunk of energy. Astronomers can measure this loss and use it as a way to weigh stars without ever touching them. The stronger the redshift, the deeper the gravitational well from which the light has climbed. The first clear terrestrial test of this effect came in the late 1950s at Harvard University, in a small 22-metre tower that has since become one of physics' quiet monuments. Robert Pound and Glenn Rebka devised an ingenious way to test Einstein's prediction here on Earth. They use gamma rays, tiny packets of extremely energetic light and aimed them down the length of the tower. According to relativity, as the light fell, it should gain energy, becoming ever so slightly bluer, while light travelling upward should lose energy, becoming redder. The difference, even over just a few floors, was so small it bordered on impossible to detect. But with exquisite precision, using what's known as the Nussbauer effect, they managed to measure it. The result matched Einstein's calculations almost perfectly. It's worth pausing to appreciate the subtlety of that experiment. The tower wasn't particularly tall, and the gamma rays changed frequency by an amount smaller than 1 part in 100 trillion. Yet the universe played along faithfully. Gravity, it seemed, really did stretch light just as Einstein had promised. This wasn't theory anymore, it was observation. The same effect that bends time and curves space could be measured in a college physics building with patient hands and clever thinking. Once scientists knew how to look, they began to find gravitational redshift in the heavens. Light from the surface of our sun shows it. Light from compact white dwarf shows it even more strongly. By measuring just how much the light's frequency shifts, astronomers can calculate how much gravity a star exerts, and therefore estimate its mass and size. It's one of the simplest but most elegant tools for probing the invisible architecture of the universe. In galaxies farther away, gravitational redshift also plays a small but telling role. The centres of massive galaxies, where dark matter and supermassive black holes dwell, warp space-time so severely that even the glow of stars around them leaves at a lower pitch of light. When astronomers compare the light from the outer parts of a galaxy to the light from its core, they can see the fingerprints of this stretching. It's not much, but it's enough to reveal how deeply the galaxy curves the space around it. To visualize it, imagine light as a small, determined climber on an endless hill of gravity. At the base, near a massive object, the climber is bright and full of energy, every step packed with momentum. As it ascends, each step costs effort. There's no wind, no friction, just the invisible slope of space-time itself. By the time it reaches the summit, it's panting slightly. Its steps longer, its rhythm slower. It hasn't lost heart, but it has lost energy, stretched thin by the climb. That is the gravitational redshift in motion, a photon catching its breath on the long way out of a star's embrace. This redshift also explains something beautifully simple. Light doesn't fall the same way that matter does, but it still feels gravity's influence. A stone thrown upward slows, stops, and falls back because gravity pulls on its mass. Light with no mass never stops or falls back, but its wavelength still stretches as it escapes. Gravity shapes both energy and geometry. Neither gets a free pass. You can even see the same principle working in reverse. When light falls toward a massive body, it doesn't slow down, it can't, but its frequency increases. The colour shifts toward blue as energy is added. That's called gravitational blue shift. It's the mirror image of the redshift, showing that gravity doesn't just stretch light, it can squeeze it too, depending on the direction of travel. In the wider cosmos, redshift is the language of distance, motion and gravity all at once. Astronomers have to separate the causes carefully. When they see light stretched from distant galaxies, they ask, is it the expansion of the universe, or the gravity of the source, or its motion through space? The answer can reveal the mass of a star, the presence of a black hole, or even the rate of cosmic growth itself. Every subtle tint of red tells a story. The gravitational redshift is one of those triumphs of science that feels almost humble. It doesn't make headlines like black holes or supernovae, but it's the quiet proof that gravity and light speak the same language. Every photon that leaves a planet, a star, or a galaxy must pay its toll in energy to escape. Most of the time, the fee is tiny, barely perceptible. But in the deep wells of massive objects, the cost becomes enormous, and light itself grows weary on the climb. So the next time you see the soft glow of a sunrise, remember that those golden rays are a little redder than when they began their journey. They've climbed out of Earth's slight gravitational pull, stretched just a fraction on their way to your eyes. It's a delicate reminder that even light, for all its speed and brilliance, is still part of this curved and patient universe. Sometimes, even photons need to stop and catch their breath. Light, for all its speed and brilliance, seems like it should be immune to gravity. After all, photons have no mass, nothing to pull on, nothing to weigh down. Yet the universe has a quiet way of humbling even its swiftest traveller. When light passes near something massive like a star or a galaxy, its path bends. It doesn't bend because the light is tugged or slowed, but because the space it moves through is curved. The photon is still following the straightest possible route. It's just that in curved space-time, straight doesn't always look straight to us. To grasp this, imagine a marble rolling across a smooth table. On a flat surface, it moves in a perfect line. But if the table sags slightly in the middle, the marble's path will curve as it follows the slope. The marble hasn't changed its mind or felt a sideways push. It's still taking the easiest route available. Space works in much the same way. When light glides past a massive object, it's not being pulled sideways. It's tracing the geometry of the curved space-time around it. Einstein predicted this in 1915 when he first completed his general theory of relativity. He calculated that light passing near the sun should bend by about 1 3/4 arc seconds, a barely noticeable angle, but one that could in principle be measured. If he was right, the positions of stars near the sun's edge during a total solar eclipse would appear slightly shifted from where they'd normally be. It was a bold claim, one that needed the rare coincidence of a clear sky, a perfect eclipse, and patient observers on the far side of the world. That chance arrived 4 years later, in May of 1919. 2 expeditions set out under the British astronomer Arthur Eddington to capture the moment. One to the island of Principe off the west coast of Africa, and another to Sobral in Brazil. As the moon slid across the sun, blocking its glare, the stars near the darkened disk came into view. Using long exposure photographic plates, Eddington and his colleagues compared the apparent positions of those stars during the eclipse with their usual positions in the night sky. When the results were developed, the stars near the sun's rim had shifted by exactly the amount Einstein had predicted. It was a quiet revolution captured in silver emulsion. The bending of starlight was the first experimental confirmation that gravity could curve space and time. Overnight, Einstein became a household name. Newspapers printed his equations as if they were poetry. Headlines read, "Lights all askew in the heavens." The universe, it seemed, had rewritten its rules. What had once been an invisible tug was now revealed as a graceful bending of geometry itself. The story didn't end there. Over the following decades, astronomers found that this bending of light wasn't confined to stars near the sun. It happens everywhere, all the time, on every scale. When light from distant galaxies passes through the curved space-time of clusters of galaxies in the foreground, the images we see from Earth can be stretched, magnified, or even multiplied. Sometimes, the alignment is so perfect that the light forms a glowing ring around the lensing galaxy, called an Einstein ring. Other times, we see delicate arcs and mirrored smears of light, the cosmic fingerprints of space-time curvature. This phenomenon, known as gravitational lensing, is now one of the most powerful tools in modern astronomy. It lets us map the invisible, dark matter, which neither emits nor absorbs light but still bends it through gravity. By studying how background galaxies are distorted, scientists can trace where mass hides, painting detailed portraits of cosmic structure. Even the most distant galaxies, whose light has travelled for billions of years, can be revealed through this natural magnifying glass. The universe, in a sense, provides its own telescope. It's easy to imagine that gravity somehow pulls on the light as it passes, but that's not quite what's happening. Gravity doesn't reach out and grab the photon. It's the space itself that's warped. The photon isn't changing its behaviour. It's just doing what it always does, travelling in a straight line through whatever space-time gives it. If space-time bends, the path bends too. The distinction might sound subtle, but it's everything. It's the difference between a force acting on light and light simply obeying geometry. A good way to picture it is to imagine a beam of light as a long ribbon stretched across space. When space-time curves near a massive object, the ribbon follows the bend like a silk scarf drifting over a round globe. The light doesn't fall into the curve, it simply moves across it, smooth and graceful, obeying the topography of the universe. What we see from a distance is a deflection, a change in direction, but to the light itself, nothing unusual has happened. It's still travelling straight ahead. This subtlety becomes clear when comparing the deflection of light to the motion of matter. A comet passing near the Sun curves because it's both pulled by gravity and moving through curved space. A photon, having no mass, only feels the geometry. It doesn't respond to gravity as a force. Yet both end up curving in a similar way, because their motion is shaped by the same warped space-time. Matter feels curvature as gravity. Light reveals curvature through its path. The amount of bending depends on how much mass is present and how close the light passes. The Sun's deflection is tiny, but near more massive objects like black holes or galaxy clusters, the effect can be dramatic. In some cases, light can even orbit a black hole several times before escaping, tracing loops in the intense curvature near the event horizon. In those moments, light becomes a dancer on the edge of geometry, balancing perfectly between freedom and capture. Gravitational lensing isn't just a cosmic curiosity, it's a window into deep time. The light that reaches us today from distant galaxies has been bent, delayed, and stretched by the matter it's passed along the way. By studying those distortions, astronomers can measure how fast the universe is expanding and even test whether Einstein's theory still holds true on the larger scales. So far, every test, every curve and arc in the sky agrees with his predictions. If you could stand in the vacuum near the Sun and watch a beam of starlight pass by, you wouldn't see it jerk or twist abruptly. It would glide, smooth and unbroken, curving almost imperceptibly as it brushed past the glowing surface before continuing into the dark. It would be like an arrow loosed from a bow, flying true yet following the natural curve of the bowstring that launched it. The path would look bent to a distant observer, but to the light itself the journey would still feel perfectly straight. That's the quiet beauty of Einstein's universe. Even light, the fastest thing there is, doesn't escape the influence of shape. It moves with the grace of a traveller tracing the contours of invisible hills, guided not by force but by geometry. And somewhere in that faint arc of starlight, bending silently across the void, the story of gravity is written in light. In the quiet rhythm of the cosmos, every planet, moon and asteroid is falling. The Earth is falling around the Sun, the Moon is falling around the Earth, and even the Sun itself is falling slowly around the centre of our galaxy. Yet none of these worlds crash into one another. They fall perfectly, perpetually, tracing elegant loops through the fabric of space-time. Each orbit is a dance of geometry, not of force, a straight line drawn across a curved map. When Newton looked at the planets, he saw a grand balance of pushes and pulls. The Sun's gravity tugged on each planet, pulling it inward, while the planet's motion tried to carry it forward in a straight line. The result was a stable orbit, an endless compromise between falling and flying. For centuries, this picture explained the heavens beautifully. But Einstein's view transformed that tug-of-war into something more serene. In his universe, the planets are not being pulled at all. They're free-falling along the straightest possible paths through the curved space-time around the Sun. It's an elegant illusion. From our human viewpoint, we see circular and elliptical orbits, as though the planets are whirling in invisible harnesses. In reality, they're doing nothing but following geometry. If space-time around the Sun were perfectly flat, the planets would drift in straight lines forever, never to return. But because the Sun's mass curves that geometry, the straightest path, a geodesic, loops back on itself. The result is an orbit, a graceful endless fall. To picture this, imagine a marble rolling across a stretched rubber sheet. Place a heavy ball in the centre, and the sheet curves downward, forming a shallow well. If you roll the marble across it, the marble doesn't head straight. It curves around the indentation, looping in wider or tighter circles depending on its speed. The marble isn't being pulled by the central ball, it's simply following the surface as it's shaped. This analogy, though popular, only hints at the truth. It captures the idea of curvature but leaves out the dimension of time, which plays an equal role in the real universe. The well isn't just in space, it's in space-time, where time itself flows differently near massive objects. Still, it's a good first glimpse of how curvature guides motion without a need for pulling. Each orbit represents a balance between motion and curvature. If a planet moves too slowly, its path spirals inward, falling toward the star. Too fast and it slips free into space. Somewhere in between lies the sweet spot where the planet keeps falling but never reaches the bottom. It's like throwing a baseball hard enough that, instead of landing, it keeps missing the ground because the Earth's surface curves away beneath it. That's all an orbit is, a continuous fall that never ends. One of the most fascinating consequences of this curved geometry appears in the orbit of Mercury, the innermost planet. Mercury races close to the Sun, where space-time is most distorted. For centuries, astronomers noticed that its elliptical orbit wasn't quite closing on itself. Each time Mercury completed a loop, the ellipse had rotated slightly, so its nearest point to the Sun, the perihelion, moved forward by a small but steady amount. It was as though the planet's orbit was slowly precessing, turning like the petals of a flower. Newton's laws could account for most of this motion by considering the tugs of other planets, especially Venus and Jupiter. But even after every known influence was subtracted, a small remainder of 43 arc-seconds per century remained unexplained. It was one of astronomy's great puzzles. Then, in 1915, Einstein's new equations solved it perfectly. The extra precession wasn't due to any hidden planet or invisible force, it was the subtle effect of the Sun's curved space-time. Mercury was faithfully following its geodesic, but the geometry itself wasn't static. It twisted ever so slightly with each orbit, and Mercury's path recorded that twist with exquisite precision. This was one of the first major triumphs of general relativity. It showed that Einstein's curved space-time wasn't just a poetic metaphor, it was measurable, predictive, and real. Every planet's orbit is affected by this curvature, though for most the difference from Newton's model is so tiny that only the most precise instruments can detect it. Mercury, being closest to the Sun, simply happens to trace the effect most clearly. Orbits aren't perfect circles, of course. They're usually ellipses slightly stretched by the balance of energy and angular momentum. The closer a planet is to its star, the deeper it sits in the gravitational valley. To stay in orbit there, it must move faster, trading time for stability. Farther out, where the valley flattens, slower motion suffices. This is why the inner planets of our solar system race swiftly around the Sun, completing their years in days or months. while the outer giants drift leisurely for decades or centuries. The geometry of space-time defines their tempo. From a mathematical point of view, this is all about energy balance. A planet in orbit has both kinetic energy, its motion, and potential energy, its position within the Sun's gravitational field. The total energy determines the shape of the orbit. Bound systems, where the total energy is negative, produce closed ellipses. Unbound systems with positive energy yield open paths, parabolas or hyperbolas, like comets visiting from the outer dark. Even these unbound travellers, though, are still following geodesics. Their paths just happen to carry them through once before they vanish into the vastness beyond. If you could see space-time directly, the Sun would not sit in the middle of a flat arena. It would sink into a four-dimensional dimple, gently warping the fabric around it. The Earth's orbit would appear as a looping ribbon winding endlessly around this curve, never descending, never rising out. Every planet, every satellite, every grain of dust follows its own winding ribbon in this same vast geometry. Even photons skim around the edges of these wells, bending slightly as they pass, echoing the same principle that guides planets. The gravity well pictures you sometimes see, those blue grids swirling around stars, are not wrong, but they miss half the story. They show space bending downward but forget that time also slows near mass. The full picture is not a sheet, but a flowing fabric, space and time stretched together. The slowing of time near the Sun is part of what keeps the planets bound, ensuring that their energy and motion remain in balance. It's a subtle, dynamic equilibrium written into the nature of space-time itself. It's tempting to think of orbits as perfect and eternal, but they are slowly changing. Tides, radiation, and the drag of interplanetary dust all cause tiny shifts. Yet, across millions of years, the same quiet truth holds. Planets move not because something pushes or pulls them, but because they are free to follow the contours of the cosmos, free to glide along the straightest possible lines, which just happen to loop forever. You can picture each orbit as a thread in a great cosmic tapestry, weaving around the Sun's curved geometry. Together, these threads form the harmony of the solar system, each one tracing its own tempo, each bound by the same geometry, yet none constrained by force. Gravity, in Einstein's world, isn't a leash, it's the pattern of the fabric itself. If you could watch the Earth from afar, not from a telescope, but from outside space-time altogether, you'd see its motion not as a circle or an ellipse, but as a helix winding through time, one full turn every year, endlessly advancing. Each orbit is a loop in both space and time, a gentle spiral that never repeats exactly because the geometry of the universe is always evolving. And so the next time you look up at the moon, remember that it's not hanging in space, it's falling, gracefully and endlessly, along the curve of space-time sculpted by the Earth. What keeps it aloft is not a force pulling upward or outward, but the simple, perfect geometry of motion. Each orbit, from Mercury's quicksilver loops to Neptune's stately drift, is a reminder that gravity doesn't command, it merely draws the lines, and everything else follows them. When light travels across the universe, it almost never takes a perfectly straight path. On its long journey through the cosmos, it threads between galaxies, slips past stars, and grazes massive clusters of matter. Each encounter leaves a faint trace on its route, a tiny curve written into the light's trajectory by the geometry of space-time itself. And sometimes, when the alignment is just right, those gentle curves turn the universe into a natural observatory, a cosmic lens crafted not by glass, but by gravity. This effect, called gravitational lensing, is one of the most beautiful consequences of Einstein's theory of general relativity. It happens whenever light from a distant object passes near something massive, like a galaxy or a cluster of galaxies, on its way to us. The gravity of the foreground object bends the path of the light, changing how the background source appears. Depending on how precise the alignment is, the result might be a faint stretching, a distorted arc, or even a perfect ring of light encircling the lensing object. The universe, in a sense, takes its own picture, photographing itself through gravity. There are several kinds of lensing, each like a different level of magnification in nature's telescope. When the alignment is perfect and the foreground mass enormous, the effect is called strong lensing. In this case, the bending of light is dramatic, creating multiple images of the same galaxy or quasar. These images can appear as glowing arcs or full rings of light, what astronomers call Einstein rings. They're named, of course, after Einstein himself, who first predicted this phenomenon in the early 1900s, though he doubted anyone would ever see it. He was right about the theory and wrong about the pessimism. Today, we have photographs of these rings, captured in extraordinary detail by the Hubble Space Telescope. When the alignment is less precise or the mass is smaller, we get weak lensing. This kind of lensing doesn't produce distinct arcs or rings, but it gently distorts the shapes of thousands of background galaxies at once. Each galaxy might look only slightly stretched or sheared, almost imperceptibly so. But when astronomers study large populations of these galaxies, a pattern emerges, a fingerprint of the invisible mass causing the distortion. By mapping these subtle stretches across the sky, scientists can reconstruct where matter lies, even if that matter doesn't emit or absorb light. In other words, weak lensing lets us see dark matter, the vast unseen substance that makes up most of the universe's mass. The third type is microlensing, which happens when a single star or planet passes in front of a background source. The lensing is so small that no arcs or multiple images appear, but the background object's brightness briefly increases as the foreground object's gravity focuses its light. Astronomers use this technique to detect exoplanets, black holes, and compact objects that would otherwise remain invisible. A tiny flicker in starlight can betray the presence of entire worlds. Each of these effects is a natural experiment, showing how mass sculpts the flow of light. The physics is elegant and straightforward. Gravity bends space-time and light follows those curves, but the results can be breathtaking. One of the most famous examples is the galaxy cluster Abell 1689. Seen through Hubble's eyes, it's a vast collection of hundreds of galaxies bound together by dark matter. Behind it lies an even more distant field of galaxies, whose light has been stretched and magnified into delicate arcs that wrap around the cluster's core. These arcs aren't artistic exaggerations, they're the literal bending of ancient light that left its source billions of years ago, only to be curved on its final approach to us. Another striking case is the lensing cluster known as MAX J 1149.5 plus 2223, which produced multiple images of a distant supernova nicknamed Refstal. The light from that exploding star was bent along several paths by the cluster's gravity, arriving at Earth at different times. Astronomers saw the same supernova flare appear, fade, and then reappear months later in another part of the sky. Light that had travelled billions of years detoured by cosmic curvature. It was the first time humanity had witnessed a single event replayed across space-time, as if the universe had recorded it for us in advance. Even individual galaxies can act as lenses, though on a smaller scale. Some of the most dramatic Einstein rings come from simple one-on-one alignments, a massive elliptical galaxy in the foreground and a bright quasar in the background. The quasar's light curves around the galaxy and reunites on the other side, forming a complete ring of illumination. These structures are astonishingly symmetrical, sometimes so perfect that they look artificial. Yet they're made not by mirrors or lenses, but by the quiet curvature of space-time itself. Gravitational lensing also helps astronomers measure the expansion rate of the universe. By comparing how light bends and how long it takes to reach us from different angles, scientists can infer cosmic distances with remarkable accuracy. It's as if nature provided a ruler that stretches from one galaxy to the next, allowing us to measure the growth of space across billions of years. To make sense of these observations, astronomers often use computer models to reconstruct the hidden mass responsible for the distortions. When they do, they find that visible matter, stars and gas, accounts for only a fraction of what's needed to explain the bending. The rest must be something unseen, something that interacts through gravity but not light. Dark matter reveals itself not by shining, but by the way it bends starlight. Without lensing, we might never have known it existed at all. The beauty of gravitational lensing lies in its subtlety. It's not a loud signal, it's a whisper written in the shapes of distant galaxies. It tells us that light, though weightless, carries the memory of every mass it passes. Every beam of starlight that reaches your eyes or your telescope has taken a unique path through the curved fabric of space-time, shaped by planets, stars, clusters, and dark halos along the way. You're seeing not just the distant source, but the whole landscape of gravity between here and there. It's easy to forget that we're participants in this phenomenon too. Earth, the Sun, and our own galaxy all bend light in small but measurable ways. Even as we look outward, our presence alters the geometry of the universe ever so slightly. The act of observing happens within the same web of curvature we're observing. In that sense, every photograph of the night sky is a collaboration between light and gravity. The next time you see an image from Hubble or the James Webb Space Telescope filled with strange arcs and glowing rings, you're looking at a moment where the universe became its own lens, its own photographer. Light that began its journey before our planet even formed has been guided, focused and revealed by the mass of galaxies that it never even touched. Those distant arcs are not distortions. They're stories of the cosmos, bent but not broken, written in light billions of years old. The universe, patient and quiet, takes its own portrait in the mirror of gravity, and what it shows us is extraordinary. A cosmos made not just of what we can see, but of what shapes the seeing itself. If you could somehow hold the universe in your hands and shake it, you'd feel it hum. Not metaphorically, literally. Space-time itself is elastic. When something truly massive happens, like two black holes colliding or neutron stars merging, the very fabric of the cosmos ripples. These ripples spread outward in every direction, stretching and squeezing space as they go. They're unimaginably faint, moving silently through everything, even your body right now. These are gravitational waves, the universe's quietest music. Einstein predicted them in 1916, just after formulating his general theory of relativity. If gravity is the curvature of space-time, then accelerating masses, like orbiting stars or spinning black holes, should create disturbances in that curvature. The idea was simple, but the consequences staggering. Every orbit, every motion, every cosmic event would send out ripples, just like a pebble dropped into a pond. But these ripples would be in space-time itself, not on water, and they would travel at the speed of light. For nearly a century, these waves were thought to be too faint to ever detect. They stretch and compress space by less than the width of a proton over kilometers of distance. Even the most energetic cosmic collisions, the kind that release more energy in a fraction of a second than all the stars in the universe combined, would barely nudge space-time here on Earth. Einstein himself doubted we'd ever be able to measure them, but physicists, as it turned out, are a patient breed. By the late 20th century, technology had caught up to imagination. Scientists built instruments so sensitive they could detect these ripples when they passed. The most famous of them are the twin LIGO detectors, short for Laser Interferometer Gravitational Wave Observatory, located in Louisiana and Washington in the United States. Each facility is shaped like a giant letter L, with 2 long tunnels, each 4 kilometers in length, forming its arms. Inside those arms, lasers bounce back and forth between mirrors, travelling the distance thousands of times. When a gravitational wave passes through, one arm is stretched ever so slightly while the other is squeezed. The change is minuscule, less than 1,000th of the width of a proton, but the interference pattern of the laser light can reveal it. It's an astonishingly delicate measurement. To give a sense of scale, imagine trying to detect a change smaller than the thickness of a human hair compared to the distance from Earth to the nearest star. Yet, in September of 2015, LIGO did exactly that. The detectors picked up a faint signal lasting just 0.2 of a second, a quick, rising chirp. What they had recorded was the final dance of 2 black holes spiralling together over 1 billion light-years away. The discovery was announced in February of 2016, almost exactly 100 years after Einstein's prediction. It was the first direct detection of gravitational waves, and it changed astrophysics forever. For the first time, we weren't just looking at the universe, we were listening to it. When scientists convert those signals into sound, what you hear is surprisingly human. A low rumble that rises rapidly in pitch before cutting off sharply, the last heartbeat of 2 massive black holes before they merge into one. Each collision has its own signature, its own timbre, depending on the masses and spins of the objects involved. These signals can tell us how far away the event was, how much energy was released, and even the nature of gravity itself. It's as though the cosmos has been broadcasting a symphony all along, but only now do we have ears sensitive enough to hear it. Every ripple that LIGO detects carries information that light can't. Some of the events that produce gravitational waves happen in complete darkness, black holes colliding in places where no light escapes. In those moments, gravitational waves become our only witnesses. They bring us news from regions of the universe that no telescope can ever see. The faintness of these signals might seem like a limitation, but it's actually part of their beauty. Because gravitational waves barely interact with matter, they pass through everything unhindered. They carry pristine information straight from their source, unaffected by dust, gas, or galaxies. A beam of light can be absorbed or scattered, but a gravitational wave slips through as effortlessly as a whisper through a dream. LIGO's twin detectors aren't the only ones listening. Other observatories, like Virgo in Italy and Kagra in Japan, have joined the network, creating a global array that can pinpoint where in the sky a wave originated. The more detectors there are, the better we can triangulate a source, like listening to thunder with ears spread across the planet. Plans for future observatories, such as the space-based LISA mission, will open our ears to even lower frequencies, revealing mergers of supermassive black holes and the slow undulations of the early universe itself. Each detection adds a new voice to the cosmic choir. We've already heard the merging of black holes, the collision of neutron stars, and even the aftermath of those collisions, shock waves of matter and energy reverberating through space-time. When 2 neutron stars merged in 2017, gravitational waves and light were observed from the same event for the first time. It was like hearing and seeing the universe play in harmony. What's remarkable is how much we can learn from a signal so brief. From less than a second of distortion, physicists can determine the masses of the black holes, their spins, their distance, and even estimate how the merged object will behave. These ripples also serve as a test of Einstein's theory under extreme conditions. So far, every chirp has fit his equations perfectly. But gravitational waves also hold secrets we haven't yet uncovered. Somewhere in the background, noise may lie echoes of exotic phenomena, primordial waves from the Big Bang, or signals from cosmic strings, or perhaps something entirely unexpected. Each passing wave is a message written in space-time itself, waiting to be decoded. It's humbling to think that these ripples are always there, passing through us unnoticed. Every second, countless gravitational waves flow through Earth, stretching and squeezing space by absurdly tiny amounts. If you could somehow see space-time flex, you'd notice everything, your room, your heartbeat, even the Earth itself, expanding and contracting by less than an atom's width. Yet it all feels perfectly still. The universe sings constantly, but we are small and our ears are new. What began as a theoretical prediction in 1916 has become a new way of observing reality. We've gone from watching the cosmos to feeling its vibrations. Light showed us what the universe looks like. Gravitational waves are teaching us how it moves, how it breathes, and how it evolves. And perhaps that's the most poetic truth of all. For billions of years, space-time has carried the echoes of creation, the songs of stars and the sighs of black holes. We've only just begun to listen. Every ripple that passes through us is a whisper from something vast and ancient. A reminder that even the emptiness between the stars is alive with motion. Even space-time can sing if you listen quietly enough. At first glance, the idea of a black hole sounds like something from a nightmare, a place where gravity grows so intense that not even light can escape. Yet, behind that dramatic reputation lies one of the most elegant creations of nature. A black hole is not a cosmic monster devouring everything in its path. It's a simple, precise consequence of geometry. When enough mass is packed into a small enough volume, space-time curves in on itself, forming a region where all paths point inward. What we call a black hole is really just the most extreme shape that space-time can take. At its heart, a black hole has two defining features, the event horizon and the singularity. The event horizon is the outer boundary, the edge of silence. It isn't a surface you could touch. There's nothing solid there. Instead, it's the point of no return, where the escape velocity equals the speed of light. Anything crossing that boundary, whether a photon or a spacecraft, is forever cut off from the outside world. Not because it's destroyed immediately, but because all possible paths lead inward from there. Deeper still lies the singularity, the central point where our equations break down. According to Einstein's mathematics, it's a place of infinite density where space-time itself collapses. In reality, physicists suspect the singularity isn't truly a point at all, but a region where the known laws of physics simply stop applying. To understand what happens there, we'd need a theory of quantum gravity, something that unites the physics of the very large with the physics of the very small. For now, the singularity remains hidden behind the event horizon, unreachable and unseeable. From a distance, however, black holes behave in surprisingly predictable ways. They can spin, they can merge, and they can even grow. The space around them follows clear mathematical patterns. A stationary black hole's geometry is described by just two numbers, its mass and its spin. That's all you need to know to predict how it will bend light and time. Despite their reputation for chaos, black holes are astonishingly simple. One of the most striking effects they produce is gravitational time dilation. To an outside observer, a clock near a black hole appears to tick slower and slower as it approaches the event horizon. Light from the falling object becomes redder, fainter, and eventually freezes just above the edge, never quite disappearing but fading into darkness. To the object itself, though, nothing unusual happens at the crossing point. It passes smoothly through, unaware that the rest of the universe has slowed to an infinite crawl. Time and space trade roles in that final descent. What looks like an end from the outside feels perfectly ordinary from within. This strange split of perspectives is one of relativity's quiet marvels. For someone watching from afar, nothing ever truly falls into a black hole. Everything just hovers at the edge, redshifted beyond sight. But from the viewpoint of the falling object, the horizon is crossed in moments, and the universe outside rushes forward in time. Both experiences are real, both consistent, and together they reveal how profoundly flexible time can be when space curves to its limits. Another common misconception is that black holes act like cosmic vacuum cleaners, sucking in everything around them. In truth, they don't. A black hole with the same mass as our Sun would bend light and time intensely nearby, but planets at Earth's distance would orbit it just as they do now. There's no mysterious suction, just gravity, obeying the same inverse square law as any other mass. It's only close to the event horizon, where space-time's curvature becomes extreme, that the familiar rules break down. The real drama near a black hole comes from tidal forces. These arise because gravity changes sharply with distance. The side of an object closer to the black hole feels a stronger pull than the far side. Near smaller black holes where the curvature is steep, this difference can be catastrophic. A person falling feet first toward the horizon would be stretched vertically and compressed horizontally, a process whimsically nicknamed spaghettification. It's not a pleasant fate, but it's important to note that it depends on the black hole's size. For supermassive black holes like those found in galactic centers, the tidal gradient near the event horizon is gentle. You could cross it without feeling a thing. Black holes are also among the most efficient engines in the universe. As matter spirals inward, it forms a hot, luminous accretion disk. Friction and magnetic fields heat this disk to millions of degrees, causing it to blaze across the electromagnetic spectrum. The energy released in this process can outshine entire galaxies. Yet the black hole itself emits nothing. It's the surrounding chaos that shines so brightly, a cosmic halo of transformation. And in an even more surprising twist, black holes aren't completely black. In the 1970s, physicist Stephen Hawking combined relativity with quantum mechanics and discovered that black holes can emit radiation. Tiny fluctuations in the vacuum near the event horizon allow pairs of virtual particles to appear briefly. Usually, they annihilate each other instantly, but if one particle falls into the black hole, while the other escapes, the escaping one carries away a little energy. To an outside observer, it looks as though the black hole is glowing faintly. This Hawking radiation is minuscule for large black holes, but it has profound implications. It means black holes can slowly lose mass, and over unimaginable timescales, evaporate entirely. For decades, black holes were purely theoretical, glimpsed only through equations and indirect evidence. Then, in 2019, the Event Horizon Telescope gave us something closer to sight. By linking radio telescopes around the world, astronomers created a virtual Earth-sized dish capable of resolving the tiny region around the supermassive black hole in the galaxy M87. The resulting image was extraordinary, a dark circular shadow surrounded by a glowing ring of hot gas. The shadow wasn't the black hole itself, it was the silhouette cast by its gravity, where light is bent so strongly that it orbits before escaping. For the first time, humanity had seen the outline of curved space-time at its most extreme. That image confirmed what decades of theory had promised. It showed that black holes are not violent holes ripping through space, but calm, mathematically perfect objects sculpted by gravity. They are the end state of massive stars, yes, but also the quiet architects of galaxies. Without them, our Milky Way might not exist at all. The one at its centre, called Sagittarius A star, anchors the orbits of hundreds of billions of stars. What sounds like destruction is in truth creation by another name. There's a quiet poetry in this. The same geometry that makes time slow to a standstill also drives the engines of cosmic evolution. Black holes recycle matter, stir galaxies, and shape the fate of light itself. They are not the villains of the universe, but its most mysterious artists, painting the cosmos with invisible brushstrokes of curvature. So the next time you see that famous image of the black hole's shadow, don't imagine a void of terror. Imagine a lens made of gravity, bending light into a halo, where time folds softly on itself. Beyond that glowing edge lies not a monster, but a masterpiece of nature's design. A place where the universe expresses, in perfect silence, the power and grace of its own geometry. When Einstein described gravity as the curvature of space-time, he gave us a universe where mass shapes geometry. But there was another layer hidden in those equations: rotation. When something massive spins, it doesn't just bend space-time, it drags it around with it. The effect is subtle, but profound, and it means that the fabric of the universe is not only curved, but can also twist. This phenomenon is called frame dragging, and it's one of the strangest consequences of general relativity. Imagine space-time not as an invisible void, but as a thick, honey-like medium. When a heavy object like a spinning planet or star rotates within it, the nearby layers of space-time are pulled along just slightly, as if the rotation were stirring the cosmic honey. The faster the spin and the denser the object, the stronger the effect. Close enough to a rotating black hole, this twisting becomes so intense that space itself begins to swirl. Frame dragging is hard to picture because it's not a force pulling on objects, it's space itself rotating. If you stood near a spinning planet, you wouldn't see the sky spin faster. The local geometry would quietly carry you with it. The axis of your gyroscope would drift, your orbit would shift, and time would take a slightly different path than expected. You wouldn't feel the twist directly, but precision instruments would. And in 2004, one of the most delicate experiments ever flown confirmed that this effect is real. That experiment was Gravity Probe B, a NASA mission launched to test Einstein's predictions about the warping and twisting of space-time around Earth. The idea was elegant. Put 4 perfectly spherical gyroscopes in orbit, spinning freely in a vacuum, and measure whether their axes of rotation gradually shift over time. If space-time were perfectly still, those axes would remain fixed forever, always pointing in the same direction relative to distant stars. But if Earth's rotation dragged space-time around with it, the gyroscope's orientation would slowly drift. Tiny, steady movements, revealing the swirl of the cosmic honey. The precision required was almost absurd. The gyroscopes were made from fused quartz, and polished so precisely that each deviated from a perfect sphere by less than 40 atomic layers. They were kept at near absolute zero to minimize vibrations and shielded from magnetic interference. Every flicker of movement, every signal from the craft, had to be measured to an accuracy of millionths of a degree. It was a feat of engineering as much as physics. For over a year, the satellite orbited Earth, quietly measuring the geometry of space, and as the data came in, the results matched Einstein's predictions. The axes of the gyroscopes had indeed shifted, by about 37,000ths of a degree per year, exactly as expected if Earth were dragging the fabric of space-time around with it. The confirmation came almost a century after the effect was first predicted, transforming frame dragging from theory into fact. It's a small number, barely perceptible, yet its implications ripple across the cosmos. Around compact, rapidly spinning objects, frame dragging becomes a dominant feature of reality. Near a rotating black hole, The effect is so strong that space itself whirls around at nearly the speed of light. In this region, known as the ergosphere, nothing can remain still. Even light is forced to move in the direction of the spin. Any object caught there must rotate with the black hole. It's like being caught in a cosmic whirlpool where the water itself is the riverbed. This twisting of space-time helps explain some of the universe's most spectacular phenomena. Many black holes and neutron stars are surrounded by disks of hot gas called accretion disks, formed as matter spirals inward. Observations show that these disks often launch powerful jets of material, shooting out along the object's spin axis at nearly the speed of light. Frame dragging is thought to play a crucial role in this alignment. As the spinning object twists space-time around it, it forces the magnetic fields in the disk to line up with its rotation, channeling energy into narrow beams that can extend for thousands of light years. These cosmic jets are among the most dramatic sights in the universe, twin streams of plasma erupting from galactic centers, shining across millions of light years. They're powered not by explosions or winds, but by geometry itself. The spin of a black hole, through frame dragging, converts rotational energy into motion and light. In a sense, the universe recycles its own angular momentum, turning spin into spectacle. Even in less extreme settings, frame dragging leaves subtle fingerprints. The orbits of satellites around Earth are affected by it, though only slightly. The Lagios satellites, passive metal spheres covered in reflectors, have been used to measure this twist by bouncing laser pulses off them and tracking the timing to millimeter precision. The results agree beautifully with general relativity, showing that even our modest planet drags the local space-time just enough to be measurable. The analogy of a spoon stirring honey captures the idea well, though the real universe behaves with more elegance. The honey doesn't swirl chaotically, it flows smoothly, predictably, shaped by the equations of relativity. If you could hover near a rapidly spinning neutron star and release two tiny spacecraft, one aligned with the spin and one against it, you'd find that the forward-moving one drifts slightly ahead of where Newtonian physics would predict, while the other lags behind. Space-time itself would be rotating, carrying the ships with it. This twisting also affects how we define rotation in a relativistic universe. In everyday life, spin is simple. An object turns relative to the space around it. But when space itself is turning, the idea becomes relative. Near a spinning black hole, even standing still requires moving, because the geometry of the region doesn't allow for absolute rest. The boundary where this begins, the edge of the ergosphere, is like the point where honey in the spoon starts to flow. Inside, resistance is futile. Everything rotates, not because of force, but because the structure of space-time demands it. The discovery and confirmation of frame dragging deepened our understanding of how dynamic and alive space-time really is. It isn't a static backdrop for cosmic events. It participates. It bends. It stretches. It ripples. And it spins. Planets twist it gently. Black holes twist it fiercely. The very geometry of the universe responds to motion, reshaping itself as objects move. And there's something profoundly beautiful about that. Every rotation, from the spin of a child's toy to the whirl of a galaxy, leaves its fingerprint on space-time. The universe is not indifferent. It feels the motion of everything within it. Frame dragging reminds us that nothing spins alone. Every movement stirs the cosmic fabric just a little, linking the dance of atoms to the spin of stars. So the next time you picture the universe, don't imagine it as a still void punctuated by moving objects. Picture it as a vast, viscous sea. Gentle currents swirling where planets turn, immense vortices twisting where black holes spin. From the smallest rotation to the grandest galactic swirl, space-time flows with it all, a silent ocean stirred by gravity's hand. Most of us go about our day without thinking about Einstein, but every time you check your phone for directions, you're relying on his equations to get you where you're going. The map app that cheerfully tells you to turn left in 200 meters is a triumph of relativity in action. Without corrections from general and special relativity, your GPS would be wrong by several kilometers within a single day. The quiet truth is that modern civilization runs on curved space-time, even if most of us never notice it. To understand how that happens, it helps to know what GPS really is. The Global Positioning System is a constellation of at least 30 satellites orbiting about 20,000 kilometers above Earth. Each satellite carries atomic clocks so precise that they would lose or gain less than a billionth of a second per day if left alone. From high orbit, these satellites continuously broadcast time signals toward the surface. Your phone receives those signals from several satellites at once and compares the arrival times. By measuring how long each signal took to reach you, it calculates your position. It sounds straightforward, but there's a catch. Those signals depend entirely on synchronized timing, and time, as Einstein showed, doesn't flow evenly everywhere. The satellites are moving fast, which means their clocks experience special relativity. Time for them ticks slightly slower than for someone standing on Earth. At the same time, they're far from the planet's surface, where gravity is weaker. According to general relativity, that makes their clocks tick faster than ours. The two effects pull in opposite directions. Special relativity slows their time by about 7 microseconds per day, while general relativity speeds it up by about 45 microseconds per day. The net result is a gain of about 38 microseconds every 24 hours. That doesn't sound like much, but when you multiply it by the speed of light, it becomes enormous, about 10 kilometers of error per day. If engineers ignored Einstein's corrections, GPS would be useless for navigation. Within a week, it would think your car was driving through buildings or floating in a nearby lake. So, before launch, satellite clocks are set to tick slightly slower than those on Earth, perfectly offsetting the relativistic effects once they reach orbit. As they circle the planet, their time runs in harmony with ours, not because time itself is uniform, but because the differences have been carefully calculated. It's an astonishing thought. Every time your phone shows your location, it's performing a relativistic negotiation. Your phone quietly consults with satellites moving thousands of kilometers above, correcting for gravitational curvature, orbital velocity, and signal delay. Each one of those adjustments depends on the same ideas Einstein wrote down over 100 years ago. In a very real sense, your phone quietly negotiates with Einstein every second. The synchronization between the satellites and the ground is one of the most delicate dances ever achieved. Every satellite carries multiple atomic clocks based on the vibrations of cesium or rubidium atoms, while ground stations monitor them from Earth and send corrections when needed. Even temperature changes, solar radiation, or subtle gravitational differences caused by Earth's shape can influence the readings. The entire system functions only because scientists understand how time bends and stretches under gravity and motion. It's not just navigation that depends on this precision. Modern communication, finance and science all rely on exact timing. Banks use atomic clocks to timestamp financial transactions down to millionths of a second. If two traders on opposite sides of the world disagree about when a transaction occurred, it can affect billions of dollars. To prevent that, global financial systems use GPS time as their universal reference. The same is true for the Internet's backbone, where routers and data centers rely on synchronized clocks to manage information flow. Every text, email, and video call owes a quiet debt to relativity. Scientific instruments too depend on accurate timing. Astronomers use time-synchronized telescopes across continents to create virtual observatories as large as the Earth itself, combining signals to study distant galaxies and black holes. Particle accelerators, deep space communications, and earthquake monitoring networks all depend on the same principle. Time must be consistent, even when the universe refuses to make it easy. One of the more poetic aspects of this is that relativity, once thought to be abstract and purely theoretical, has become an everyday utility. In Einstein's time, the equations of general relativity were admired for their beauty, but few imagined they'd one day guide delivery trucks or locate lost pets. Today, they are baked into the algorithms of your smartphone, invisibly correcting the distortions of curved space-time so that your map app stays honest. If you could somehow turn off those corrections, the results would be immediate. After a few minutes, your phone's position would drift by tens of meters. After an hour, you'd be off by several hundred. After a day, the discrepancy would grow to 10 kilometers or more. You could be standing in your driveway while your GPS swears you're in another town. The system only works because we understand how space and time bend under motion and mass, and because we've learned how to compensate for it. This might make you wonder, if time flows differently depending on altitude and motion, does that mean astronauts age differently? In a small but measurable way, yes. Astronauts aboard the International Space Station experience both effects at once. They orbit Earth at around 27,000 kilometers per hour, which slows their clock slightly due to special relativity. But they're also about 400 kilometers above the surface, where gravity is weaker, which speeds their clocks up due to general relativity. The two nearly balance, leaving them aging a tiny bit slower than those on Earth, about a few milliseconds behind after 6 months in orbit. It's a human-scale reminder that the geometry of time never stops ticking at its own pace. In some sense, the world's entire technological network now rests on a truce between theory and reality. We design machines to behave as if space-time were flat, even though it isn't. Every correction in the GPS system is like a whispered apology to Einstein. You were right. We'll fix it. The equations that once described Mercury's orbit or bending starlight now underpin delivery routes, weather forecasting and rescue missions. And it doesn't stop there. As our clocks become even more precise, measuring down to trillionths of a second, we're beginning to use them not just to navigate, but to map gravity itself. Differences in tick rates can reveal subtle changes in Earth's gravitational field, helping scientists study groundwater movement, volcanic activity, and even the melting of ice sheets. In the near future, relativity won't just guide us through space, it will let us watch the planet breathe. It's a humbling thought that our world now depends on a theory born from pure curiosity. Einstein wasn't trying to make navigation systems or banking networks work more smoothly. He was trying to understand the nature of reality. Yet his vision now runs quietly beneath nearly everything we do. So, the next time your phone pings a location or tells you the quickest route home, remember the invisible physics beneath your fingertips. Behind that glowing map is a symphony of satellites, lasers and atoms all keeping time on a curved planet in a curved universe. Your phone doesn't just find your position, it reconciles you with the fabric of space-time itself. And as you move from one point to another, guided by those invisible signals, you're participating in one of the most extraordinary collaborations in history, a conversation between everyday life and the geometry of the cosmos, whispered 1 microsecond at a time. When Einstein first revealed that gravity was the bending of space and time, he did more than rewrite physics. He gave us a new way to imagine the universe. Suddenly, space wasn't an empty stage where things happened. It was an active participant, bending and flexing in response to matter and energy. But there's another layer to that story, one that stretches beyond stars and galaxies. the universe itself, taken as a whole, also has a shape. Just as space-time curves locally around planets and stars, it can also curve globally, across billions of light-years. The difference between these two kinds of curvature, local and cosmic, is one of the most subtle and beautiful ideas in modern cosmology. Local curvature is familiar now. It's the kind of bending that keeps planets orbiting stars and galaxies bound together. Around every massive object, space-time dips slightly, forming a local pocket of curvature. If you could see it, you might imagine a dim, translucent grid bowing gently under the weight of a galaxy, like silk stretched by a bead of dew. Each star and planet creates its own tiny indentation, rippling the surrounding fabric. But beyond these local dips and valleys lies a much larger question. What happens when you zoom out far enough to look at the universe as a whole? If you could somehow step outside the cosmos and observe it all at once, would the fabric of space itself appear curved, like the surface of a sphere? Would it be open, like a saddle, curving outward? Or would it be perfectly flat with no overall bend at all? Einstein's equations allow for all three possibilities: closed, open, or flat, depending on the total amount of matter and energy the universe contains. A closed universe is like the surface of a sphere. Travel far enough in one direction, and in principle, you could end up back where you started. It's finite but unbounded. No edges, no walls, just a cosmic loop. An open universe, on the other hand, is more like a saddle, curving outward forever. It has no boundaries but continues expanding eternally, with galaxies drifting farther and farther apart. A flat universe lies delicately between the two. Parallel lines stay parallel. The angles of a cosmic triangle add up to 180 degrees. An expansion proceeds at just the right rate to balance matter's pull and the universe's push. The remarkable thing is that, for all its vastness and complexity, the universe's overall curvature comes down to one number: its density. If the total density of matter and energy is greater than a certain critical value, space will be closed. If it's lower, space will be open. If it's exactly equal, the universe is flat. Cosmologists sometimes call this the cosmic Goldilocks problem. Too much density and gravity eventually halts expansion, leading to a future collapse. Too little, and the universe expands forever, thinning into silence. Just right, and it expands steadily without ever tearing itself apart. So how do we measure something as abstract as the curvature of all space? The answer lies in the oldest light in existence, the cosmic microwave background, or CMB. This faint radiation is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The CMB is filled with tiny fluctuations, slight variations in temperature and density that seeded all the galaxies and clusters we see today. The patterns of those fluctuations are affected by the geometry of space. If the universe is closed, the light from distant regions converges slightly as it travels, making the patterns appear larger. If it's open, the light diverges, making them appear smaller. By mapping the CMB with exquisite precision, satellites like WMAP and Planck have given us the answer. On the largest scales we can observe, the universe appears astonishingly close to flat. The margin of error is less than 1%. That means, if you drew a triangle with sides spanning billions of light years, its angles would add up to almost exactly 180 degrees. Space, it seems, doesn't curve much at all when you look across the entire cosmos. But almost flat isn't the same as perfectly flat. There may still be a gentle arch to the cosmic grid, so slight that it would take a universe far larger than the observable one to detect. Even a small curvature could have deep implications for how the universe began and how it might end. And of course, flatness on a global scale doesn't erase local curvature. Galaxies still sit in their own dimples, stars still bend starlight, and black holes still twist space into whirlpools. The cosmic fabric is flat overall, but richly textured in detail, smooth on average, but rippled with structure. It's also important to remember that the expansion of space is not the same as the stretching of things. This distinction often causes confusion. When cosmologists say that space is expanding, they don't mean that galaxies themselves are inflating like balloons, or that atoms are growing larger. The forces that hold matter together, electromagnetism, gravity, nuclear bonds, are far stronger than the gentle stretching of cosmic expansion. Instead, it's the space between galaxies that grows. Distant clusters aren't flying through space like shrapnel from an explosion. They're carried apart because the space itself is increasing. You can imagine galaxies as dots on the surface of a balloon. As the balloon inflates, the dots move away from one another, not because they're travelling across the surface, but because the surface itself is expanding. The same thing happens in 3 dimensions. From any given galaxy's point of view, all others appear to be receding, yet no one spot is the centre. Expansion is uniform. It happens everywhere at once, even in regions where space is nearly flat. The discovery that space expands came from Edwin Hubble in the 1920s, when he noticed that distant galaxies' light was redshifted. The farther away they were, the faster they seemed to recede. Einstein initially disliked the idea. He had once introduced a cosmological constant to keep the universe static, but observations forced him to accept that space itself was dynamic, and that the universe had likely begun from a hot, dense state. The echoes of that beginning are what we see today in the cosmic microwave background, still faintly warming the sky in every direction. Modern measurements continue to refine our understanding of the universe's shape and fate. The large-scale structure of galaxies, their filaments, clusters and voids, also reflects the underlying curvature. On a map of billions of galaxies, the cosmic web appears as a faint grid, gently arching here and there but remaining mostly smooth. Dark matter provides the scaffolding, while dark energy, that mysterious pressure accelerating expansion, determines how the web evolves. Together they ensure that the universe's geometry is not just a snapshot, but a living process. If you could visualize it, you might picture a dim grid stretching endlessly, dotted with bright knots of galaxies. Each knot sits in a small depression, a local well of curvature, while the overall grid remains gently arched, almost imperceptibly. The universe, then, is both flat and curved, depending on how closely you look. Zoom in, and you see the dips around stars and planets. Zoom out, and the fabric smooths to near perfection. This layered geometry gives the cosmos a quiet balance. Local curves give rise to motion and structure, planets, stars, and life itself, while global flatness allows the universe to endure, expanding gracefully rather than collapsing or tearing apart. Einstein's equations describe both in one continuous story, from the swirl of a black hole to the shape of everything. It's easy to forget amid the vastness that the space you inhabit right now is part of that same geometry. The atoms in your body, the air around you, the distance to the nearest star, all are written on this same cosmic grid. You live within the curvature of space-time, and that curvature stretches as far as the imagination can go. The universe may be nearly flat, but it's anything but empty. It's a grand, gently bent expanse that still hums with the memory of its own creation. When Albert Einstein published his general theory of relativity in 1915, it was such a radical departure from everything that came before that even he wasn't entirely sure how it would hold up. The equations were beautiful, elegant, compact, and profound. But beauty alone doesn't make a theory true. It needed to face the one test that no idea, no matter how brilliant, can avoid nature itself. Einstein proposed that gravity wasn't a mysterious pull acting across space, but the curvature of space-time caused by mass and energy. The mathematics seemed to fit, but it would take experiments and observations to see if this curved universe matched the one we live in. Over the next century, general relativity would pass every challenge thrown at it, from sunlight to lasers, from planets to black holes. Yet the story of how it earned its credibility begins with just 4 simple, daring predictions. The first test was the bending of light by gravity, the one that made Einstein famous overnight. In Newton's world, light shouldn't bend at all since it has no mass. But in Einstein's curved space-time, light must follow the same path that everything else does. He calculated that a beam of starlight passing near the sun should deflect by about 1 3/4 arc-seconds. It was a tiny angle, equivalent to seeing a coin shift the width of a hair from several meters away, but measurable. In 1919, British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During those precious minutes when the sun's glare was hidden, his team photographed the stars surrounding the darkened disk. When they compared the positions of those stars to where they normally appeared in the sky, they found exactly what Einstein had predicted. The light had bent. Newspapers declared a new era in physics. Lights all askew in the heavens. It was the first time humanity had seen the curvature of space-time drawn across the sky. The second test came from Mercury's orbit. For decades, astronomers had puzzled over the fact that Mercury's elliptical path around the Sun didn't quite close on itself. Each orbit shifted slightly, causing the point of closest approach, the perihelion, to creep forward. Most of the shift could be explained by the gravitational tugs of other planets, but there was a small leftover of 43 arc-seconds per century that Newton's laws couldn't account for. Einstein applied his equations to Mercury's motion and found that space-time curvature near the Sun perfectly explained the discrepancy. Without changing a single observation, the new theory resolved a mystery that had lingered for generations. The third test involved gravitational redshift, the idea that light loses energy as it climbs out of a gravitational field. Einstein predicted that a clock deeper in gravity's well would run more slowly than one farther away, and that light escaping from a massive body would stretch to longer wavelengths, appearing slightly redder. The first confirmation came in 1959, when physicists Robert Pound and Glenn Rebka at Harvard University measured a subtle shift in the frequency of gamma rays sent between the top and bottom of a tower. The effect was minute but unmistakable. Gravity was altering the passage of time, exactly as relativity said it would. The fourth classic test came from the delay of radio signals passing near the Sun, known as the Shapiro delay. In the 1960s, astronomer Erwin Shapiro realized that if space is curved, then light or radio waves traveling near a massive object should take slightly longer to reach their destination than they would through flat space. When he sent radar signals bouncing off planets, the returning echoes were delayed by just the right amount. Once again, Einstein's equations held perfectly. Those 4 tests established general relativity as the foundation of modern physics. But the story didn't end there. It only deepened. As technology improved, scientists found new ways to push the theory further, measuring its predictions with greater and greater precision. Atomic clocks, for instance, have confirmed gravitational time dilation down to astonishing accuracy. By comparing clocks on mountaintops with those at sea level, researchers have measured differences of just a few nanoseconds, a blink of time so small that it would have seemed impossible to detect a century ago. Yet those tiny shifts are exactly what Einstein foresaw. Time, it turns out, is as malleable as the space it inhabits. Space probes have also tested relativity in the vast laboratories of the solar system. The Cassini spacecraft orbiting Saturn used radio signals to measure how light bends as it passes near the Sun. The results matched Einstein's predictions to within a few parts in 100,000. Even the motion of entire galaxies, tracked by radio telescopes, shows how space-time curves on colossal scales. And then there are the lasers, modern experiments that push the limits of sensitivity. The LIGO observatories, which first detected gravitational waves in 2015, rely on lasers to measure changes smaller than 1,000th of a proton's width. When those detectors caught the faint chirp from two colliding black holes, it wasn't just a triumph of engineering, it was the ultimate confirmation that space-time behaves like a flexible medium, capable of vibrating and ringing. Einstein had predicted those waves in 1916, but it took nearly a century of technological progress to hear them. What's remarkable is that no contradiction has ever been found. Every test, from the bending of starlight to the ticking of atomic clocks, has confirmed general relativity's predictions. It's one of the most thoroughly verified theories in science. And yet physicists know it can't be the full story. Relativity describes the universe on large scales: stars, galaxies, and gravity wells. Quantum mechanics, on the other hand, governs the very small: atoms, particles, and forces. Both are stunningly successful, but they don't quite fit together. At the heart of a black hole, or in the first instant after the Big Bang, the equations of relativity predict infinities that make no physical sense. Somewhere beyond our current reach, a deeper theory must reconcile the two. That tension is what keeps scientists testing, refining, and questioning. Even the most successful theories aren't sacred. They're stepping stones toward better understanding. Einstein himself once said that no number of experiments can prove him right, but a single one could prove him wrong. More than a century later, physicists continue to look for that one experiment, an anomaly, a deviation, a clue that might point beyond. Today, researchers are searching for those limits with tools Einstein could never have imagined. They study how gravity behaves near neutron stars, how black holes merge, how dark energy influences cosmic expansion, and whether tiny deviations might appear in the paths of orbiting spacecraft. So far, relativity has passed every challenge, but science lives by the rule of confidence without finality. The more precisely we measure, the more opportunities we create to be surprised. It's a curious irony that a theory born from the abstraction of mathematics has become so deeply woven into the fabric of daily life. From GPS satellites adjusting for time dilation, to gravitational waves rippling through detectors, general relativity has proven both durable and indispensable, yet its greatest strength may be its openness to doubt. Einstein's equations describe a universe that is both elegant and imperfectly known, a universe that invites curiosity rather than closure. So the next time you hear about a new experiment testing gravity, remember that it's not about proving Einstein right once again. It's about listening closely for the moment when the universe might whisper something new. For more than a century, two great theories have described the universe with astonishing success: general relativity and quantum mechanics. One governs the very large, where planets orbit stars and galaxies bend light. The other rules the very small, where particles flicker into and out of existence and uncertainty is the only certainty. Each works flawlessly in its own domain, yet they refuse to speak the same language. When gravity and quantum effects meet, inside black holes or at the dawn of the universe, the mathematics falls apart. It's as though reality itself is written in two dialects that become unintelligible when read together. Einstein's theory gives us a universe made of smooth, continuous geometry. Space and time form a seamless fabric that can bend, stretch, and ripple. Quantum mechanics, on the other hand, tells us that everything, even energy, comes in discrete chunks. Quanta. It's probabilistic, jittery, and inherently uncertain. The trouble begins when we try to describe space-time itself using quantum rules. What happens when the fabric of the cosmos is examined so closely that it stops looking smooth and begins to shimmer? To see why this matters, imagine zooming in on space-time far beyond what any microscope could reach, past atoms, past protons, down to the Planck scale, about 10 to the minus 35 meters. That's roughly 100 billion times smaller than a proton. At that level, according to most physicists, the concept of a continuous spacetime stops making sense. The smooth curves of Einstein's geometry give way to something granular, chaotic, and alive with fluctuations. Space itself might foam and bubble like boiling water. Distances and times could lose their fixed meaning. In that seething quantum mist, gravity and quantum mechanics collide. A theory of quantum gravity would reconcile these two descriptions, showing how space-time behaves when both quantum uncertainty and curvature matter equally. It would explain what happens at the center of a black hole, where general relativity predicts infinite density, but quantum physics demands otherwise. It could also reveal how the universe began, when all of space was compressed into an unimaginably hot, dense state. In short, it would describe the ultimate fabric of reality, where geometry and quantum energy are one and the same. Physicists have spent decades trying to find that theory, and several promising ideas have emerged, each elegant in its own way. One of the most famous is string theory, which proposes that the fundamental building blocks of the universe aren't point-like particles at all, but tiny vibrating strings. The different modes of vibration correspond to different particles: electrons, quarks, photons, even gravitons, the hypothetical carriers of gravity. In this picture, space-time and matter are made of the same underlying stuff, just expressed in different notes of vibration. The mathematics of string theory naturally includes gravity, and it unites the forces of nature into one grand framework. The catch? It requires extra dimensions, 10 or sometimes 11, and those dimensions must be curled up so tightly that we can't detect them. Another approach, loop quantum gravity, takes a different route. Instead of adding dimensions, it quantizes space-time directly. In this theory, space is woven from finite loops of energy, forming an intricate network called a spin foam. Distances, areas, and volumes aren't continuous but come in discrete steps, like pixels on a screen. The geometry of space becomes digital rather than analog. At larger scales, those loops blend together, creating the smooth space-time of Einstein's equations. Loop quantum gravity doesn't need strings or extra dimensions. It simply suggests that the universe has a smallest possible unit of space. Then there are more radical ideas still. Some physicists think that space-time itself isn't fundamental, that it might emerge from something deeper. In this view, geometry could be a collective illusion, like temperature or pressure, which only appear when countless microscopic entities interact. Perhaps space-time arises from networks of quantum information, tiny relationships of cause and effect that, when viewed from afar, resemble a smooth fabric. If that's true, then gravity isn't a basic force at all, but a statistical outcome of how information organizes itself. This idea, called emergent spacetime, turns everything upside down. It suggests that space and time are not the stage for physics, but the byproduct of it. The equations that describe curvature might be the large-scale shadow of something much stranger. A hidden code written in quantum bits. The holographic principle, for example, proposes that everything inside a region of space could be fully described by information encoded on its boundary, just as a hologram on a flat surface creates a three-dimensional image. In that case, the entire universe could be a kind of cosmic projection, with geometry emerging from the mathematics of information. Each of these ideas, strings, loops, emergent geometry, offers glimpses of the same goal, a world where quantum and curvature are not rivals but partners, yet none has been proven, and perhaps none is the full story. Experiments at these scales are almost impossible. The Planck length is far beyond the reach of any particle accelerator, and even the most energetic cosmic rays barely graze it. For now, quantum gravity remains a theory we can imagine more easily than test. Still, hints appear in the strangest places. The behaviour of black holes, for instance, seems to link geometry, thermodynamics, and quantum information in mysterious ways. Stephen Hawking's discovery of black hole radiation showed that they're not truly black. They leak energy, and over immense timescales they evaporate. That process suggests a deep connection between entropy, information, and gravity. In recent years, physicists studying entanglement, the quantum correlation that links particles across distance, have found patterns that seem to reconstruct the shape of space itself. The more entangled two regions are, the more tightly they appear to be connected in geometry. It's as if space-time grows out of relationships, not locations. If that sounds philosophical, it's because it is. The quest for quantum gravity isn't just about equations, it's about what we mean by reality. In Einstein's world, space and time are the most fundamental things imaginable. In the quantum world, they might be negotiable, temporary conveniences that dissolve under scrutiny. Perhaps the universe is not a fabric but a weave, not a stage but a story told in interactions. Physicists joke that finding the theory of everything is like reading the fine print of existence. General relativity gave us the grand curves, quantum mechanics gave us the jittery detail, and quantum gravity might show how the two fit together, though the print may be very, very small indeed. Or, as one theorist once put it, even space might need smaller print. Until we can test these ideas directly, we live in a fascinating middle ground. On one hand, the universe behaves with the smooth elegance of Einstein's geometry. On the other, its foundations whisper of something granular, pixelated and strange. Every orbiting planet and every flickering particle is part of the same cosmic puzzle, waiting for a theory to join them. So far, the universe hasn't contradicted either side. Relativity and quantum mechanics remain undefeated in their domains, two masterpieces that overlap only in mystery. But one day, in the heart of a black hole or the light from the first instant of creation, the small and the vast may finally meet. And when they do, the universe might reveal not just its shape, but the deeper logic from which shape itself arises, a place where geometry, energy and information are all the same thing, written in the hidden handwriting of the cosmos. When we think of a straight line, we imagine something simple, direct, uncompromising and absolute. From a child's ruler to the beam of a laser, straightness feels like the most basic feature of the world. But in the geometry of the universe, straight is not a fixed idea. It's a relationship, an agreement between space and time about what it means to move without turning. The straightest possible path may look curved, and what appears bent to our eyes might be perfectly straight to the cosmos. In Einstein's space-time, the shortest path between 2 points is called a geodesic. It's the route that an object takes when it's under no force, when it's simply following the shape of space-time itself. For a beam of light travelling through curved geometry, that means gliding smoothly along the contours carved by gravity. For a planet orbiting a star, it means falling endlessly around it, tracing a loop that, in four-dimensional space-time, is as straight as can be. It's a humbling reminder that straightness isn't about rigidity, it's about harmony with the landscape. A train moving on curving tracks isn't bending from the perspective of the ground it follows, it's staying true to its rails. In the same way, the path of a falling apple or a circling moon is straight within the geometry of space-time. The The curve is only in our perspective. This idea unsettles our everyday intuition, because human perception evolved in a world where space seems flat. For most of history, geometry meant Euclid's geometry, the geometry of lines, angles, and right triangles that holds true on a sheet of paper or a carpenter's table. Parallel lines never meet. The angles of a triangle add up to 180 degrees, and the shortest distance between 2 points is a straight segment. Everything about our senses supports that view. Our eyes and brains assume that space is linear because, at the scale of human experience, it is. It wasn't until mathematicians like Gauss, Lobachevsky and Riemann in the 19th century that anyone seriously considered non-Euclidean geometries, worlds where straight lines could converge or diverge, where the very rules of distance and angle could change. Their ideas seemed like pure abstraction, the kind of mathematical dream that might never touch physical reality. Then Einstein came along and showed that nature had been non-Euclidean all along. Gravity in his picture isn't a force acting on things. It's the geometry of space and time telling them how to move. The straightest paths are those that follow that geometry exactly, even when they look curved to us. What we once called bending is simply the faithful obedience of matter to the structure of reality. And yet, even knowing this, our minds still cling to the Euclidean picture. It's deeply rooted in how we see and move. Our brains evolved to make quick judgments about trajectories, where to throw a stone, how to walk a straight line, when to duck. Over millennia, the assumption of flatness became a cognitive default. The Earth feels flat underfoot, the sky looks like a dome, and the horizon seems to stretch forever in a straight line. Non-Euclidean geometry is true, but it's not intuitive. Philosophically, that realization reshapes how we think about truth itself. The universe isn't made of absolute straight lines, it's made of relationships. Geometry at its core is relational. Distance, angle, and direction only make sense within a framework, relative to the curvature of space-time and the observer's motion through it. What's straight to one traveller may appear bent to another. In this sense, reality is not a fixed structure, but a dialogue between perspective and geometry, a harmony of motion and shape. Even perception itself reflects this relational truth. The straight lines in your field of vision are curved by your eyes. The retina maps a spherical world onto a flat surface, and your brain reinterprets it as linear. You live constantly in a world that is both curved and straight, reconciled through experience. Your mind is already performing a quiet version of Einstein's geometry every time you open your eyes. This dance between perception and reality has long fascinated philosophers. Kant argued that space and time might be forms of human intuition, ways the mind organizes experience rather than external things in themselves. Einstein's work gave that idea a new twist. Geometry is not imposed by the mind alone, but by matter and energy as well. The universe shapes our perception, because it literally shapes the space through which we perceive. If that sounds abstract, think of the everyday miracle of walking in a straight line. You follow what feels like a simple trajectory, but your body is really tracing a geodesic across a spinning planet, in a solar system curving through galactic space, in a galaxy sliding through the fabric of an expanding universe. The straightness you feel beneath your feet is a local truth nested within cosmic curvature. Straight lines exist, but only locally, only provisionally. Beyond your immediate horizon, every line eventually bends. Once you begin to see this, the universe takes on a kind of quiet poetry. Geometry stops being a set of rules and becomes a language of relationships. Curvature, once seen as distortion, becomes beauty, an expression of harmony between motion and shape. The orbits of planets, the arcs of rainbows, the waves of light, all are examples of nature's preference for curves. The universe doesn't fight against bending, it embraces it. It's not just physics that has learned to appreciate this. Artists and architects too have always known that curves speak more deeply than straight lines. From the domes of ancient temples to the spirals of seashells, curvature feels alive. Straight lines convey order and control, curves convey grace and motion. Even the human body follows this rule. There are no perfect lines, only soft arcs and flowing contours. Nature seems to agree with Einstein. The universe prefers grace over rigidity. Curvature also teaches a kind of humility. The straight lines we draw, whether in geometry, art or thought, are simplifications of something richer. They work beautifully when the scale is small and the landscape simple, but the closer we look, the more we see the underlying curve. Every straight path eventually meets its limit, whether in physics or philosophy. Reality, it seems, has no perfectly flat surfaces. Perhaps that's why Einstein's insight feels less like a revolution and more like a revelation. It didn't destroy our old notion of space, it deepened it. It showed that geometry is alive, that straightness and curvature are not opposites but partners in the same cosmic conversation. Every time a planet or a photon moves, it's participating in that dialogue, tracing a line that's both straight and curved depending on how you look. So maybe straightness was never the goal. The universe doesn't insist on rigidity, it moves in harmony with itself. Curvature isn't a flaw, it's a signature, a gentle bow of the cosmic fabric acknowledging that nothing travels alone, not even light. In the end, the lesson is a quiet one. What we call straight is simply the simplest path through a curved reality, and that reality, vast and intricate, prefers softness to sharpness, rhythm to stiffness, grace to perfection. The lines of the universe are written in curves, and if we learn to read them, we may find that even geometry has poetry hidden in its heart. If the story of space-time has taught us anything, it's that the universe still holds more curves than we can see. Every generation of observers has thought they'd reached the limits of discovery, only for the next to find new layers of structure hidden in the dark. Einstein gave us the mathematics to describe those curves, but the map is far from complete. Space still whispers secrets, and our instruments are only just beginning to hear them clearly. In the coming decades, a new fleet of observatories will take humanity's measurements of curvature to extraordinary precision. Among them is LISA, the Laser Interferometer Space Antenna, a gravitational wave observatory that will float in space instead of resting on Earth. Where LIGO listens for short, high-pitched chirps from colliding black holes, LISA will hear the deeper, slower notes. The long drawn-out ripples of supermassive black holes spiraling together across millions of light-years. 3 spacecraft will form a triangle 5 million kilometers on each side, linked by lasers measuring the distance between them to a fraction of an atom. As gravitational waves pass through, they'll stretch and compress that enormous triangle, revealing the soft base of the universe's geometry in motion. Then there's the Square Kilometre Array, or SKA, a radio telescope so vast it will span continents, with thousands of antennas scattered across Australia and South Africa. Working together, they'll form a single giant ear capable of mapping cosmic structure with exquisite accuracy. The SKA will chart the distribution of galaxies and gas, tracing the slow drape of curvature across billions of light-years. Its sensitivity will help scientists test whether space truly is as flat as current data suggest, or whether there are faint ripples, subtle global curves that even the cosmic microwave background has missed. Closer to home, next-generation clock networks are emerging as some of the most precise scientific tools ever made. Atomic clocks have already verified time dilation and gravitational redshift to astonishing levels. But the newest designs, optical lattice clocks, are pushing the limits further. These clocks are so accurate that they could detect a difference in gravitational potential between your head and your feet. When linked together across Earth and in orbit, they'll form a relativistic web of timekeeping, sensitive enough to map variations in Earth's gravity field in real time. They could even detect passing gravitational waves by spotting the tiniest coordinated blips in time itself. Each of these instruments, LISA, SKA, the global clock network, serves as a kind of stethoscope pressed against space-time. The goal isn't just to confirm Einstein's equations again, but to listen for the faint murmur of something new. Subtle discrepancies might reveal how gravity behaves at the smallest scales, or how dark energy guides the universe's expansion. They might even hint at the global topology of space, whether the cosmos loops back on itself, curls in extra dimensions, or stretches infinitely with hidden symmetry. Dark energy, that mysterious pressure driving the acceleration of cosmic expansion, remains one of the greatest enigmas in science. Is it a property of space itself, a kind of elastic tension in the cosmic fabric? Or is it a sign that our understanding of gravity breaks down at vast distances? Precision mapping of curvature could help distinguish between these possibilities. If space bends slightly differently than Einstein's equations predict, it might point toward new physics, perhaps even the fingerprints of quantum gravity at work on cosmic scales. Meanwhile, gravitational wave astronomy is set to open entirely new windows on the universe. With space-based detectors like LISA, we'll be able to trace not just violent collisions but slow dances, the gradual inspirals of black holes, the rhythmic hum of binary stars, and even the faint background chorus of waves left over from the earliest moments after the Big Bang. Those primordial ripples could carry direct evidence of how the universe inflated and cooled, offering a glimpse into physics at energies we'll never reproduce on Earth. The more precisely we measure curvature, the more the universe surprises us. It's not just about confirming what we already know, but about finding the cracks where knowledge begins to bend. Each improvement in sensitivity, whether through radio dishes, laser arms, or atomic oscillations, peels back another layer of subtlety. We might one day detect that space isn't perfectly uniform, that its fabric has texture, perhaps shaped by quantum fluctuations frozen from the early cosmos. Even if these explorations don't uncover entirely new laws, they'll still enrich our understanding of the old ones. Precise measurements of gravitational waves and curvature have direct down-to-earth benefits. The same technologies that let scientists detect space-time ripples also refine GPS navigation, improve earthquake detection, and synchronize global communication networks. The pursuit of cosmic precision quietly enhances everything from space travel to climate science. The universe's grand geometry turns out to be useful for keeping our own world in order, and yet, for all the progress we make, space retains a quiet sense of mystery. There's something endlessly graceful about a reality that can never be completely mapped. The more finely we measure its curves, the more we find new depths to them, like tracing the edge of a spiral only to discover it goes on forever. The universe seems to fold away its last secrets just out of reach, not to taunt us, but to keep curiosity alive. That curiosity is, in a way, our species' soft gravity. It pulls us forward, gently but insistently, toward better instruments, sharper questions, and deeper understanding. We orbit the unknown much like planets around a star, bound not by fear of the dark, but by fascination with what it hides. From cave paintings of constellations to lasers measuring space-time ripples, that same urge has guided us across centuries to make the invisible visible, the distant familiar, the abstract tangible. Perhaps the greatest discovery yet to come won't be a new law of physics, but a renewed sense of wonder, that the universe is still unfinished in our minds. Every new observatory, Every refined clock adds another thread to our picture of reality, and still the tapestry grows larger than we imagined. So the next time you look at the night sky, remember that those stars and galaxies aren't fixed points on a backdrop. They're marks on a living fabric, slowly curving, expanding and whispering stories we've only begun to hear. Space is still bending, time is still unfolding, and our understanding is still in orbit around the unknown. The future of curvature is the future of curiosity itself, and as long as we keep asking, the universe will keep answering, sometimes with equations, sometimes with silence, and always with one more curve waiting just beyond what we can see. Tonight we followed a simple idea to its quiet horizon. Matter writes the map, and motion reads it. Planets, photons, and people do not need to be told what to do. They glide along the shapes already inscribed in space and time. Gravity, then, is not a tug but a pattern. Curves in the fabric that guide every step and every beam of light. Once you see it, the universe feels less like a machine and more like a landscape, and motion becomes the art of taking the gentlest path available. Return for a moment to the river we first imagined. The water does not argue with the valley, it moves where the valley allows, so too with light and with us. Starlight flows along invisible bends, skimming past suns, arcing around clusters, braiding faintly through the cosmic web. Planets drift as leaf boats on that same current, their orbits not forced but permitted by the shape beneath. Even time enters the stream. Where mass gathers, the current slackens. Where space opens, it runs a little freer. To notice this is to trade drama for clarity, and to find a deeper wonder in the quiet precision of it all. The beauty of these curves is how democratic they are. A clock on a mountain, a satellite in orbit, a photon leaving a distant star. Each obeys the same soft rule. The differences are matters of degree, not of kind. From the smallest tick of an atomic clock to the long song of a gravitational wave, the story is continuous. Curvature guides, motion responds, and the universe keeps its own time with extraordinary patience. It is comforting to know that nothing here relies on haste. Geometry is calm by nature. It does not rush to explain itself, yet everywhere it allows you to feel its presence. In a map that stays true, in a signal that arrives when it should, in a night sky whose patterns are ancient and reliable. If your mind drifts as you listen, that is perfectly fine. These ideas are good company for drowsy thoughts. They do not demand attention so much as reward it, like constellations emerging slowly when the eyes adjust. If the river metaphor has done its work, you might picture all travel, of light, of planets, of thoughts, as smooth motion along a graceful bed. There are no sharp commands, only soft constraints. The cosmos does not insist, it invites, and that invitation extends to rest. Somewhere above, starlight still travels those gentle curves. Somewhere above, entire galaxies are reading the same map, their spirals and arcs written by the same hand that draws the moon's path across our sky. Before you drift off, a small kindness to the algorithmic winds. If this helped you unwind, feel free to subscribe for more calm explorations of the cosmos. Your quiet presence here keeps these journeys possible. For those already aboard, thank you, truly. If you'd like a gentle nudge when the next night sailing begins, tap the bell so the river finds you again. Now let the edges of the day soften. Let the ideas loosen their grip and settle like dust in a sunbeam. The map will still be here in the morning, and its curves will still be kind. Light will keep moving, planets will keep falling perfectly, and time will continue its unhurried drift. You do not need to hold any of it. The universe breathes quietly, sleep well beneath its curve,